this one here. So what we're going to do is we're going to graph this. Now, even though all we're really concerned about is end behavior, one thing I do want to do here is I actually want to, we don't want to zoom. Now, zoom in or out. Now, the reason is zeros, any real zeros that I give you will always be between negative and positive 10. Now, let's putz with the y values a bit, and let's see if that does something for us. Oh, beautiful. Oh, man, that is awesome. So what I'm going to do is I am going to actually copy this over to my paper, just as we see it here. And so what we see here, now what was the degree of this polynomial? It was a third degree polynomial. Now it does cross the x-axis 3 times. Now how many turning points does this have? It has 2 turning points. It can have no more than n-1 number of turning points. So if this were a 4th degree, it could have 3 turning points. So in other words, the purpose of this here, we see our turning points, we see our zeros. What we know is there's going to be no behavior changes to the left or to the right. So as x goes to negative infinity, where is y going to go? Positive infinity. Or up. And again, you'll be asked to circle this. Now, as x goes to positive infinity, y is going to go to negative infinity. That's all. So we could have also realized, hey, that's an odd degree, and the leading term is negative. And since that's the case here, that's why the end behavior is what it is. Now, it's obvious that 1, 2, 3, 4, 5 is one of my roots. If I hit the trace button, yeah, I could see that x equals 5 is one of my roots. Now, if I try to do negative 1, let's see, negative 1 is another root. Now, there is a third root, which is not an integer. But if we're having a little trouble seeing that, guess what we get to break out? The polynomial root finder. Da-da-da. Third degree. And we enter the coefficients, negative 2, 5, 22, and 15. And there we are, negative 3 halves.
This is probably a dumb question, but how do you get there on the calculator?
It's under apps, and you choose the polynomial simultaneous one. I'll go back to that in just a couple of seconds here. So I'm going to go to main, and I'm actually going to quit because I'm going to come right back to it. So under applications, you should see polysimul 2, which on this one is number 7. It might be another number on other calculators. Then you get to polynomial root finder. Oh, someone. Okay, what I'm going to have to do on my calculators is put it back on there. So I'm actually going to go do that when I go to my office hour. So x is going to be negative 3 halves, by the way. And if we go to the graph on here, we see that negative 3/2, which is negative 1.5, yeah, there's our other root. Now, before too long, we'll actually be able to use this calculator to find the minimum and maximum points, and in turn, any intervals of increase and decrease. But we're just going to focus on the zeros for the most part. So, that's how it all works. Any other questions on this? Again, no dumb questions. About the intermediate value theorem, and I'm not really going to go too deep with this, but basically what the intermediate value theorem does for us is, given two values, a and b, that if f of a and f of b have opposite signs, then there has to be at least one root between a and b. So for this, what you're going to do is, for f of x equal to this, we're going to find f of 2 and f of 4. So basically, all you're going to do here is replace the x with 2 and with 4. And if they have different signs, then that means there is a real root between them. So f of 2, that would be 2 cubed minus 5 times 2 squared minus 29 times 2 plus 105. So when we use a calculator to figure that out, we get, what do you get? It's 35. Now, f of 4, basically just replace any and all x's with 4. And for that, we get negative 27. So therefore, since f of 2 and f of 4 have opposite signs, there is a real zero between x equal to 2 and x equal to 4. Spoiler alert, I believe it's 3. If you do f of 3, let's see. So yeah, 3 to the third minus 5 times 3 squared minus 29 times 3 plus 105, that's 0. Is 3 between 2 and 4? Yeah. So that's basically how the intermediate value theorem works. Read things properly. We're now going to get into one of the more difficult operations of algebra, and that's polynomial division. So we're going to look at simply dividing polynomials by a monomial. And then we're going to get into long division of polynomials. And then ultimately synthetic division. So for this first one, if we have 10x to the third minus 15x to the second plus 10x, and it's all divided by 5x, all you have to do is divide each individual term by 5x. So 10x to the third over 5x is what? Ten x to the third over divided by 5x. It's going to be 2x squared. Now, one thing is, yeah, you have to subtract an exponent there. So that's what will happen. 15x squared divided by 5x is going to be what? 3x. And 10x divided by 5x. And that's 2. All right, not bad. So you can write out the individual operations here. I'm going to do that here. 48x squared over 8x minus 16x to the third over 8x plus 24x over 8x. So 48x squared over 8x simplifies to what? That's 6x minus 2x to the second plus 3. Now, I would personally accept this, but if you had an instructor that was pushing wanted descending order, this second part is in descending order. So now we're going to divide each of these terms by 10x squared. And let's just leave them as fractions. So 45x to the fourth over 10x squared, that's going to become what? So 45 over 10, which becomes 9 halves. 9 halves x squared minus, now 25 over 10 is 5 halves. Divide the numerator and denominator by 5, so we get 5 halves x, and after that is plus 1. Now, of course, I'm not going to give you problems like this on a test because basically you just need to make sure you can do this basic stuff. Now, there is a video in the library that shows you how, in the video library on YouTube, that shows you how to do this kind of operations in the preliminary. Now, we're going to get into dividing polynomials by polynomials. Now, it is going to be a lot of work. Now, the way I'm going to write it out is going to seem lengthy, but it's going to give you a reference for everything you need to know. Now, if 8 times 5 was 40, the factors of 40 were 8 and 5. So 40 divided by 5 would be what? 8. 40 divided by 8 would be 5. So, if the product of x minus 3 and x plus 5 gives you x squared plus 2x minus 15. Now, if we divided by x minus 3, what would the quotient be? It would be x plus 5. Because if you divide by one of the factors, you get the other factor. And it's going to follow that if we divided by x plus 5, what would the quotient be in that case? X minus 3. Now, in a couple of minutes, we are going to do the polynomial division. Now, so before we get into the actual polynomial, let's do a long division here of a number. 553 divided by 4. Well, 4 goes into 5 how many times? 1 time. So, 1 times 4 is 4. So then we get 1, and after that, you get this. Now, 4 goes into 15 how many times? 3 times. Well, 3 times 4 is 12. And basically, we bring this down. Now, 4 goes into 33 how many times? 8 times. Well, what was 8 times 4? 32. So basically, this was 138 with a remainder of 1, or we could express it as 138 and 1/4. There's your remainder and what you divided by, 4. Now, the first couple of these are going to have no remainder. So, now we honestly already know what the quotient is going to be for this. It's going to be x plus 5. But we're going to work through this. Now, so what I'm going to do here is off to the side, I'm going to have a scratch pad of sorts. So it's not, you can't just divide the first term and the first term by x, then the next term by -3. No. But we always do the leading term over the leading term. So x squared is going to be divided by x. Now, what's the quotient of that? It is x. Now, another thing I'm going to do here, this x will need to be multiplied by x minus 3. And that is going to be x squared minus 3x minus x squared minus 3x. Now, I'm going to teach you a method that is not in your textbook. I'm going to give credit to a former student of mine for coming up with this, named Logan Buzzard. And I taught her at Perry McClure High School. Here's the thing. The way I learned how to do this long division would be to put this in my head. Okay, that becomes a negative x squared, and this becomes a positive 3x. And Logan said, Mr. Jarrett, why not just write it down? Like, that is a good idea. So basically, we distribute this as a negative, so we get minus x squared plus 3x. And then we can just kind of cross this out. X squared minus x squared is what? Just nothing. That all has gone bye-bye. Now 2x plus 3x is 5x. Now we're going to bring down the negative 15. Now we're going to do our next round of division. What's the leading term of this? 5x. That leading term is 5x, and we're going to divide it by x. Remember, divide leading term by leading term. So 5x divided by x is 5. And it's positive 5. Now, we need to do the 5 times the x minus 3, which gives us 5x minus 15. So we subtract 5x minus 15, or as Logan would do, Logan Buzzard. I liked her last name, so that's why I call it Buzzard. Yeah, it's just a cool name. Negative 5x plus 15, this is gone. So 5x minus 5x, that's nothing. Negative 15 plus 15 is 0. Now, the fact that there was a remainder of 0 basically meant that this was a perfect factor. Now, am I going to make you write out all this stuff? No. I am doing that to show you where everything comes from. That is the reason I'm doing this. So we start off liter by liter, x squared over x, which is x. And then x gets multiplied by x plus 5. And we get x squared plus 5x. And yeah, x squared minus x squared, that. And yeah, the old way, you'd have to do 2x, but that becomes minus 5x. And you could probably have done this without Logan's method. But whenever you're getting, like if you're dividing by a trinomial, Logan's method will be a lot. You'll thank her for that. But I'm going to do this with her method no matter what. Negative x squared minus 5x. So 2x minus 5x, well, that's negative 3x. And minus 15. So then we're going to do liter by liter once more. What is negative 3x over x? Negative 3. So negative 3 times x plus 5. Now, if you notice, I'm changing colors here, too. That will help you, too. So we get negative 3x minus 15. Oh, I forgot to put the minus 3 here. That's pretty darn important. So, of minus negative 3x minus 15. Now see, Logan Buzzard's method would really be helpful here, because you're dealing with a lot of sign changes now. So double negative, well, that makes it positive 3x plus 15. Well, guess what? It don't matter anyway because it's all 0. So the quotient is simply x minus 3. All right, so that's how it all works. Now, what do you notice about the degrees here? The degree of the dividend, which is 2. Now the divisor, which is 1. Now the quotient, what was the degree of the quotient? That was 1. So basically, you ended up subtracting degrees. All right, I'm going to let you try this next one. Hit on this first one. So basically, liter by liter, x squared over x is simply x. Then x times x minus 1 will equal x squared minus 1x. So we get minus x squared minus 1x, and distributing, you get negative x squared plus 1x. This is gone. Now, x squareds cancel out. That's the purpose of the division here. That's why we do that. Now, 2x plus 1x, that's 3x. And then I'm going to draw an arrow to indicate, minus 3. So we do 3x over x, which is 3. 3 times x minus 1 is 3x minus 3. So basically, if this is the same thing, there's going to be no remainder. But I'm going to write this out all the way. Our next one will have a remainder. So negative 3x plus 3. Gone. So x plus 3. So the quotient is simply x plus 3. The remainder is nothing. Have a remainder. So let's do it to it. Liter by liter, x to the third over x is what? X squared. So we'll go ahead and put the x squared here. So x squared times x plus 3 is x to the third plus 3x squared. So then we get minus x to the third minus 3x squared. So negative x squared minus 3x squared, well, guess what? That's negative 4x squared. And we need to bring down the next term, minus 4x. Now, since this is just a binomial, we don't really need to bring down the 11, although we could. It really makes no difference. I'm going to bring it down. Is it hurting you to bring it down? No. So then, negative 4x squared over x is what? Negative 4x. And so negative 4x times x plus 3 is negative 4x squared minus 12x. So distributing this, we end up getting positive 4x squared plus 12x. So this just goes by the wayside. Negative 4x plus 12x is 8x plus 11. Now we do, oops, I'm going to change the color on that. We now do 8x over x, which is 8. So we now get 8 times x plus 3, which is 8x plus 24. So minus 8x plus 24, negative 8x minus 24. And we get negative 13. So what happens here now, we actually have a quotient of x squared minus 4x plus 8. And the remainder, you can write it as negative 13 or negative 13 over x plus 3. So basically, degrees, you still subtract. Because if we divide a third degree by a first degree, what would the degree of the quotient need to be? Three minus 1. That's why it's a second degree. Now that's going to come into play in a little bit, particularly whenever we do synthetic division. Let's start up on this one. So 8x to the third, 8x to the third over 2x, that's going to be 4x squared. So 4x squared times 2x minus 7 is going to be 8x to the third minus 28x squared. Then, distributing everything, plus 28x squared. Draw that little line here. So negative 38 plus 28, that's minus 10x. Oh wait, no, negative 10x goes down here. And that will be negative 10x squared. Then plus 53x minus 76. So then we got another liter by liter. Negative 10x squared over 2x, that's going to be negative 5x. And negative 5x times all this That's 2x minus 7. That would be negative 10x squared plus 35x. So double negative, well, that's positive. So you have positive 10x squared minus 35x. So 53 minus 35, well, that's 18x. And don't forget minus 76. So we get one more round, liter by liter, 18x over 2x, which is 9. Now, so yeah, 9 is the last constant term, so here's the thing. We've got our quotient, but we're going to get a remainder out of this, which is going to be 18x minus 63 minus 63, negative 18x plus 63. So basically, our remainder is negative 13. So the quotient is 4x squared minus 5x plus 9, and the remainder is negative 13, or negative 13 over 2x minus 7. All right. Let's do it. So 3x to the 4th over x squared, that's going to be 3x squared. So we'll get 3x squared here, and then 3x squared times x squared minus 5x plus 3. That's going to be 3x to the 4th minus 15x squared plus, 15x to the 3rd here, plus 9x squared. And then distributing, see, yeah, this is where distributing really helps. Plus 15x to the 3rd minus 9x squared. So that's all gone. You get negative 4x to the 3rd. 30 minus 9, well, that's 21 x to the 2nd. And I'll just kind of keep the arrow here. Minus 16x plus 1 as well. So then we get negative 4x to the 3rd over x to the 2nd, which gives you negative 4x. And then negative 4x times all of this. That's going to be negative 4x to the 3rd plus 20x to the 2nd minus 12x. So double negative, that's going to make it positive 4x to the 3rd minus 20x to the 2nd plus 12x. So the cubes are gone. We get x squared minus 4x plus 1. Don't forget the 1. Then, let's see what else we do here. Well, let's do x squared over x squared. That's just 1. So what's happened here, ends here. So now, minus x squared minus 5x plus 3 minus x squared plus 5x minus 3 and we get x minus 2. So the quotient is 3x squared minus 4x plus 1. Now the remainder is x minus 2 or x minus 2 over x squared minus 5x plus 3. Now, this is going to come into play in our final unit, especially when we get into partial fractions. But for now, we're just going to leave it like this. This is a lot. What's wrong with this is there's no middle term. We're going to write this as 3x squared plus 0x minus 8 for a placeholder. Trust me, that's going to make your life a lot easier. Minus 37x to the third minus 13x to the second plus 56x minus 86. All right, maybe a couple moments. All right, so 6x to the fifth divided by 3x squared, well, that's going to be 2x to the third. So 2x to the third times all of this is 6x to the fifth plus, well, 0x to the fourth. But see, there's a good reason why I put this placeholder in. Because if you just did that minus 8, you could have put that here and it wouldn't line up. And that would be minus 16x to the third. So negative 6x to the fifth plus 16x to the third. So we get 15x to the fourth minus 21x to the third minus 13x to the second. So then here's another round of division. 15x to the fourth divided by 3x squared, that's going to be 5x to the second, or 5x squared. So 5x squared times all of this is 15x to the fourth plus 0x to the third minus 40x to the second, or negative 15x to the fourth minus 0x to the third plus 40x squared. So what happens here is that's all gone. So we get negative 21x to the third plus 27x squared plus 56x. So then we need to do the 21x to the third, negative 21x to the third divided by 3x squared. That is going to be negative 7x. So negative 7x times all of that is negative 21x to the third minus 0x squared plus 56x. And then redistributing, get positive 21x to the third plus 0x squared minus 56x so we get 27x to the second plus 0x minus 86. And so 27x squared over 3x squared, it's 9. So 27x squared plus 0x minus 72, or negative 27x squared minus 0x plus 72. And we're left with negative 14. So here is your quotient, and your remainder is negative 14. Or negative 14 over 3x squared minus 8. Division is actually going to be easier. Now, we're only going to be able to use synthetic division to divide by linear or first degree polynomials. Now, there is synthetic division of higher order polynomials. Now, that is above our pay grade. But you can do all this. You can do, higher order synthetic division. But we're only going to focus on linear. Now, we're going to divide this by, we're going to divide x squared plus 2x minus 15 by x minus 3. Now, we know the quotient is x plus 5. We knew that. Now, what value would make x minus 3 equal to 0? Well, x equals 3. So whatever that value is goes in that box. Now, these are the coefficients of the divisor in descending order. 1x squared plus 2x minus 15. Now, here's how we do synthetic division. So this first one always gets brought down. 1. Now, 3 times 1 is 3. And that's what comes out here. Now, rather than subtracting, we're going to add. So what is 2 plus 3? 5. Now, what is 3 times 5? And what is negative 15 plus 15? 0. Now, so basically, since we divided a second degree by a first degree, well, for synthetic division, we're always going to lose just 1 degree. So basically, the quotient is 1x plus 5. And the remainder is 0. Now, wasn't that a lot quicker? Well, with that in mind, we're going to work through another one. So, what's going to go into this box? Negative 2. That's right. Now, the coefficients in descending order are 2, 8, 7, and negative 2. Now, you always bring that first one down, so we have a 2 here. Let me rewrite that. What is negative 2 times 2? So the negative 4 is what comes here. What is 8 plus negative 4? That's right. Negative 2 times 4 is negative 8. 7 plus negative 8 is negative 2 times negative 1 is, and negative 2 plus 2 is 0. So now the quotient is going to be 2x to what power? To the second. Because if we divided a third degree by first degree, it's going to start as a second degree. And then it'll be plus 4x minus 1. All right, I'm going to let you try that now. So what's going to go into the little box here? Positive 1. We'll have a 3, negative 8, 9, negative 5, and 10. So that first 3 always, the first term just comes down, so that's a 3. 1 times 3 is 3. Negative 8 plus 3 is negative 5. 1 times negative 5 is negative 5. 9 minus 5 is 4. 1 times 4 is 4. Negative 5 plus 4 is negative 1. And negative 1 times 1 is negative 1. 10 minus 1 is 9. So the quotient is 3x to the correct minus 5x to the second plus 4x minus 1. And the remainder is 9. Or you could do it as 9 over x minus 1. All right. There's an example that's not on your notes, but I just put it there. We're going to go through that one because it has a bit of a significance to it. You'll see why in just a minute. So what will go into the box? Negative 3. We'll have 1, negative 1, negative 4, and I think that should actually be positive 11. So we'll have that first 1. Negative 3 times 1 is negative 3. That's negative 4. This will be 12. Negative 4 plus 12 is 8. And negative 24, and that's negative 13. So the quotient is x squared minus 4x plus 8. And the remainder was negative 13. Now, there was a reason as to why I did this particular problem. We already did this with long division. We go and take a look here. X squared minus 4x plus 8. So, yeah, it goes to show that if we're dividing by something like that, we can use either synthetic or long division. All right. Another situation where if we arrive at a special case such as this, where there might be no x squared term, there might be a missing term, you have to use a placeholder. So since we are dividing by x minus 3, a 3 is going to go in here, and it'll be 3, 0, negative 28, and 3. So 3 is 3. 3 times 3 is 9. 0 plus 9 is 9. We get 27, which is negative 1. 3 times negative 1 is negative 3, and 0. So the quotient is 3x to the second plus 9x minus 1. And the remainder is 0. Now the significance here, since the remainder is 0, what this means is 3x to the third minus 28x plus 3 equals x minus 3 times 3x squared plus 9x minus 1. Straight up. Now, you don't have to write that out, but since the remainder was 0, we had a situation where it was indeed a perfect factorization. All right, I want you to do the next two, and that's going to be it. So for this first one, obviously a 5 will go in here of a 1x to the third, but how many zeros will follow? 0x squared, 0x, negative 125. So we get a 1, 5 times 1 is 5, 0 and 5 is 5, 5 times 5 is 25, 0 plus 25 is 25, 5 times 25 is positive 125. So the quotient is x squared plus 5x plus 25, and the remainder is 0. So basically, x to the third minus 125 equaled x minus 5 times x squared plus 5x plus 25. Basically, a difference of cubes factoring. If you remember that, you learned how to factor differences of cubes. So we got a negative 2 in here, x to the fourth, 0x to the third, 5x squared, 0x, negative 36. The first one comes down, negative 2 times 1 is negative 2. We got a 4 here, that's a 9, negative 18, positive 36. So the quotient is x to the third minus 2x to the second plus 9x minus 18. And this is where we'll stop it for today. All right, so let's go ahead and do this. I'm not going to worry about the scratch pad here. The 12x to the fifth divided by 3x squared, that is going to be 4x to the third. So then we multiply this 4x to the third by everything. We get 12x to the fifth minus 20x to the fourth plus 4x to the third. So negative 12x to the fifth plus 20x to the fourth minus 4x to the third. So that's all gone. So then we get negative 6x to the fourth plus 25x to the third minus 54x squared. So then negative 6x to the fourth over 3x squared, well, that's negative 2x squared. So negative 2x squared times 3x, well, 3x squared, that's negative 6x to the fourth plus 10x to the third minus 2x to the second. So that's positive 6x to the fourth minus 10x to the third plus 2x to the second. So we get 15x to the third minus 52x to the second plus 56x. All right, So 15x to the third divided by 3x to the second, that is going to be 5x. So then we multiply 5x by everything. 15x to the third minus 25x to the second plus 5x. So negative 15x to the third plus 25x to the second minus 5x. So negative 52 plus 25, that would be negative 27x squared plus 51x minus 11. This 11 that we bring on down. So, last part here, negative 27x squared divided by 3x squared, well, that is just going to be negative 9. So, negative 9 times all of this is negative 27x to the second plus 45x minus 9, or plus 27x squared minus 45x plus 9. Ultimately, we get 6x minus 2. So we've got our quotient of 4x to the third minus 2x to the second plus 5x minus 9, and the remainder of 6x minus 2, or 6x minus 2 over 3x squared minus 5x plus 1. All right, so that is what we get. Is I want to go ahead and discuss some more synthetic division here. So this idea looks somewhat scary, but in reality, it's not. So what we have to do here, we have to find out what makes 2x plus 3 equal to 0. Now, it's true, we could make it a decimal, or, we'll just leave it as a fraction. So you get 2x equal to negative 3, x will equal negative 3/2. So that is what is going to go inside the box. We get 6, 17, 18, and 9. Now, you're going to find something a little different about this one in just a couple of moments here. Now, effectively, what we are really doing is, this is 2 times x plus 3/2. And what's happening here is negative 3/2 is what makes that, makes our factor 0. So then we bring everything down, start with the 6. 6 times negative 3/2, that's negative 18/2, that's negative 9. 17 minus 9 is 8. So what happens here, 8 times negative 3/2, that's negative 24/2, or negative 12. And then we get 6 here. Well, 6 times negative 3/2 is negative 9. Now, what happens here is the quotient is 6x squared plus 8x plus 6. Now, that's if we divided this by, x plus 3/2. Now, what can I factor out of the quotient? I can factor a whole 2 out of that quotient. So that'll give me 2 times 3x squared plus 4x plus 3. And then, that is, again, that is multiplied by x plus 3 halves. Now, what I'm going to do with this x plus 3 halves is I'm going to move it out front. (3x squared plus 4x plus 3). But we can multiply out by the 2 here. So ultimately, we get 2x plus 3 times this. This is the factorization, 3x squared plus 4x plus 3. Fact that x minus 3 is a factor of this. Now, what happens here, and I'm going to start giving you, I'm going to give you something where I'll give you one of the factors, and then you'll be expected to find the other corresponding factors and zeros. So, if x minus 3 is a factor of this, what would be a corresponding zero of this? X equals what is a 0? X equals 3. Very good. Now, here is what's going to happen. Now, can you all see this okay up here?
Yes, a little smaller.
It is smaller, yes. Now, I'm curious. I wonder if that other, I'll tell you, when I taught at Southern Wayne, I had 2 LCD projectors, one in the front, one in the back, and I'll tell you, that was like awesomeness. Actually, yeah. But, well, anyway, so I'll touch it back in a minute or two. But here's the thing. We're going to put 3 in here. Now, we'll have 2, -7, -33, and 108. Now, what's going to happen here, if x minus 3 is indeed a factor, the remainder is going to be 0. Now, what you're going to get here is a quotient. We bring this first 2 down. 3 times 2 is 6. We get -1. 3 times -1 is -3. We get -36 out of this. 3 times -36 is -108. And bless you, it's 0. So, here's what happens now. The factorization would be x minus 3 times 2x squared minus x minus 36. Now, here's the thing. This is what we call the depressed quadratic or depressed polynomial. Now, here's the thing. We're going to get depressed quadratics to start with. Now, here's the thing. This is what we're now going to set equal to 0. So you're going to set 2x squared minus x minus 36 equal to 0. And solve that. So you'll do that, and then we'll see what happens. We could, and since the leading term is something that is not 1, what we can just do is factor this. I need 2 numbers that have a sum of -1 and a product of -72. What are they? Negative 9, positive 8. So then we get 2x squared minus 9x plus 8x minus 36. Factor by grouping, x times 2x minus 9 plus 4 times 2x minus 9. X plus 4 and 2x minus 9 now equaling 0. So basically, x will equal negative 4. X will also equal to 9/2. So here's what happens. I'm going to ask you, the zeros are x equals 3. So what happens is, in a little bit, you are going to have to find one of those zeros in some way. But, we're going to crawl before we walk here. X equal to negative 4 and x equal to 9/2. The factorization, x minus 3 times x plus 4 times 2x minus 9. So we will use the polynomial root finder just to verify some things. This is a third order. We enter the coefficients as 2, negative 7, negative 33, and 108. There's your zeros. Now, the zeros are not always going to be entirely rational. So, if negative 4 is a zero of this, now, we can put negative 4 into the polynomial. We get 1, negative 2, 1, and 100. Now, what will happen is the remainder should be 0. So we bring down this first 1, negative 4 times 1, that's negative 4. That's going to be negative 6. And negative 4 times negative 6 is positive 24. And then we get 25 out of this, negative 100, and that's 0. So now, the depressed quadratic is x squared minus 6x plus 25, which we now have to set equal to 0 and solve. So, in the words of Gary Gilmore, let's do it. Let's complete the square on this. Oh, this is interesting. Half of negative 6 is what? Negative 3. And negative 3 squared is 9. We get x minus 3 quantity squared equaling negative 16. Uh-oh. I think we're getting some imaginary zeros here. Well, yeah, we are. But that's okay. So let's take the square root of both sides. X minus 3 will equal plus or minus 4i. X will equal 3 plus or minus 4i. Now, here's the thing. if we wanted to write this in factored form, factored form would simply be x plus 4 times x squared minus 6x plus 25. And the reason for that is simply zeros are not rational. Or even real for that matter. Now, thing is, there's no radicals involved in this, so if I actually go to coefficients and type them in, that would be 1, -2, 1 and 100, now we get -4 here. Now, I might have to actually go back. Oh, if I go to a plus bi, now I do it. Yeah, see, we get these. Now, if the zeros involved radicals, it would not give them to you in simplest radical form. It would give them to you as a decimal. But here's the other thing we're going to do. We're going to graph this. So I'm going to quit this app. And that is x to the third minus 2x squared plus x plus 100. Now, even though we really don't need to, I'm actually going to change the Ymin and Ymax to zoom it out a bit. We're not going to actually use the zoom in and out, though. So here's the thing. This is a third-degree polynomial. You would have expected it to cross the x-axis 3 times. But imaginary zeros do not cross the axis. I'm trying to wake you all up here. I'm getting my... So, yeah, we get -4 here. And notice that basically it doesn't even have a turning point. Yeah, it could have had it at the most 2. Fundamental theorem of algebra. It states that a polynomial function of degree n has n number of complex, meaning real or imaginary roots. Now what that means is these roots can be real or imaginary. Now, roots can occur more than once, and they would count for multiple roots in that sense. So, with that in mind, let's think about this. So, I've given you some examples here. X to the third plus 14x to the second, 63x to 90. Should have 3 complex zeros because it's a third degree. This one would have 3 complex zeros, and they are 7, 2i, -2i. Imaginary numbers do count as zeros. Also, when the coefficients are real and rational, which they always will be, anytime you have a complex zero, its conjugate has to be a 0. So if you go back real quick, 3 plus 4i was one of the roots. So it stands to show that 3 minus 4i must also be a root. Now, another example here, x to the fourth minus 7x to the third plus 12x to the second plus 4x minus 16 should have 4 complex zeros. However, we see only 3 distinct ones. The 2 would actually occur twice, so that it counts for 2 zeros. And since it occurs twice, we could say it has a multiplicity of 2. So what we're going to do here is we're going to take the polynomial and reduce it. You're going to strip it down. Insert the stripper theme music. You know, the band music. No. Yeah, I don't know if you ever. I'll have to play that. It's just stupid like big band music. Once we get it down to a quadratic, that's our surefire method. Because then we can complete the square and use the quadratic formula. So, you know, if we find a 0, x minus 0 is a corresponding factor. And so the depressed polynomial is brought down, and then the factorization, and that's what we get here. So for this one, I'm not giving you any information. And so you're probably thinking, oh, what the heck? Why do we have to do that? Well, guess what? You have to find one of the zeros and bring it down. But here's the thing. So I am going to use my root finder and find one of them, because if it's a third degree, chances are it could be, you know, one of those roots will be rational. In fact, all three will be rational. So I'm going to use my root finder to find one of the roots. So let's punch it up on that wonderful graphing calculator. Let's see, we get 1x to the third minus 8x to the second. So that is -8. Minus 25x plus 200. And we find them, oh, we have all three real roots. Now, I'm going to show you something really cool. So, we do have three roots. We could use either one of them to break it down. The roots are x equals 8, x equals -5, and x equal to +5. Now, what we would do is we would take one of those and do a synthetic substitution. If we did that, we would get the quadratic that gives us the other zeros. So here's the thing, and you're probably going to think this is extra work, but you know what? It's easy stuff. It's quadratic equations. They're fun. So if we took out x equals 8 versus, you know, x equal to -5 versus x equal to +5. We're going to get a different depressed quadratic each time. However, that depressed quadratic would give us the other two roots. So if I enter, you know, x equal to 8, put an 8 in here, and that's 1, -8, -25, and 200. We did it for -5, and it's still 1, -8, -25, and 200. And if we did it for +5, 1, -8, -25, and then 200. So let's do it for this first one. Well, 8 times 1 is 8. That's 0. That's 0. And it's -200 for 0. So the depressed quadratic is x squared minus 25. You set that equal to 0. Well, hey, that's a difference of squares. So since that is a difference of squares, that'll just be, x minus 5 and x plus 5 equal to 0. So x will equal to 5 and negative 5 for the other roots. All right, see? Not bad. Now, if we did the same thing here, we'll see what the other roots are in this order. It's all pretty cool how it works out. Okay. All right. My wife was introducing me to one of her friends this weekend, and she's like, "Yeah, it's my husband. He's pretty smart. He's like Sheldon Cooper, but in a Peter Griffin body." I'm like, Negative 5 times 1 is negative 5. We get negative 13. And negative 13 times negative 5 is 65. We get 40. Then negative 200. 0 there. So x squared minus 13x plus 40 equals 0. Hey, guess what? That factors into x minus 8 and x minus 5. So x equaling 8 and x equaling 5 are the other roots. Now, you won't always have the luxury of seeing something like this or seeing it in this way, because one of the, chances are the other zeros will probably just not work. I mean, not work, but they won't be rational like this one. So you get the 1, 5 times 1 is 5. You get negative 3, 5 times negative 3, that's negative 15. That's negative 40, and then negative 200. And that's 0 again. X squared minus 3x minus 40 equals 0. This is going to factor into x minus 8 and x plus 5 equaling 0. X equaling 8 and x equaling negative 5 are the others. So here's the thing. The ultimate factorization is x minus 8, x plus 5, x minus 5. Now, am I going to make you do this for all three? No, I will not. Because you have other things to do. Like what? Go out and watch Family Guy, That's a good show. Simpsons, they're just not as funny, though. Now, if we graph this original polynomial, so we are going to get x to the third minus 8x squared minus 25x plus 200. Now, if I actually type in the factored form, that would be x minus 8, x plus 5, x minus 5. Now, watch this. Same thing. So we know it works. Now, possible rational zeros before we take our break, even though we started a little late, we'll still do our break here as normal. Possible rational zeros, given a polynomial of the nth degree, there's your general form. You need to look at the leading term coefficient of a sub n and our constant of a sub 0. Now, if we divide, we have to consider all factors of both our leading term coefficient and our constant. We list our factors and then divide all the factors appropriately. Now, we're going to get several possibilities. Now, what happens is these are all possible rational zeros. Now, any of these values can be a rational zero. Now, if any zero is a rational zero, it's restricted to this form. Now, you're probably thinking, what the heck, why can't we just use the calculator? Well, here's the thing. This is one thing they used to do before graphing calculators. What they would do is they would list all possible rational zeros, and you do synthetic substitution and punch each one in until you got a hit. So, if we want to find the actual zeros of this polynomial, let's use that root finder again. Yeah, root finder is a great thing. Of course, we're not always going to do it here, but we'll get 2 and -3, -11, and 6. 3, -2, and 1/2. So, the constant term is 6. The leading term coefficient is 2. So the factors of the constant term would be ±1, ±2, ±3, ±6. Now, factors of the leading term would just be ±1 or ±2. Now, what happens now is we take all the factors of leading term and divide them by the constant. Actually, it should be constant over the leading term. And there will be repeats, and there's going to be a whole boatload of possibilities. But we'll do that after the break. So basically, we could do 6/1, 6/2, 3/1, ±3/2, 2/1, or 2/2, and then 2/1, 1/1, 1/2. So this is just ±6, ±3, and that's already a 3, so we don't have to do anything. 3/2, 1, 2/2 is 1, 2/1 is 2, well, we already have a 1 there, and then 1/2. So basically, we have 12 possible rational zeros. Now, what happens here is, there's 12 possibilities. Back in the old days, you would have been told to find, plug in random rational zeros until you've got a hit. But basically, this limits it to the possibilities. All the actual zeros, all 3 of the actuals, all 3 of the actual zeros were in the list. Now, are all of our possible rational zeros actually zeros? No way. Because, well, that's 12 possibilities. So, in other words, x equal to 4 could not be a 0. That's just a random example. Now, all bets are off for irrational zeros, if there are any irrational zeros or imaginary zeros. So that's how that'll work. All right. Basically, it goes to show that for any rational zero, it has to be of that form, P over Q. So I want you to list all possibles for this one, and then find the zeros using methods previously. So basically, we would be taking the factors of negative 36 over the factors of 1. So basically, we don't have to do, a whole lot here. So basically, factors of 36 are plus or minus 1, plus or minus 2, 3, 4, 6 is not, 7, 8, 9. And here's a way to remember it. 4 times 9, 3 and 12, 2 and 18, and 1 and 36. So those are just the possible rational zeros. Now what we're going to do is we are going to find the zeros using methods learned previously. So what we can do is, graphically use the root finder. Do you find any of the rational zeros? Do you have one of them? X equals 4 is one of them. Now, here's the thing. In order for this to be an actual zero, the remainder would need to be 0. What did I put there? So 4 times 1 is 4. 4 times 0 is 0. 4 times 9 is positive 36. So x equals 4 is a 0. So now x squared plus 9 equal to 0. So then you have to solve that. Well, guess what? That's going to be imaginary. That's going to give you some imaginary zeros. So x squared will equal negative 9. X will be plus or minus 3i. So we get 3 zeros out of this. X equal to 4, 3i, and negative 3i. Now, negative and positive 3i are what of each other? Conjugates. So, if we want to do a factored form, well, that's actually very easy. X equals 4, that corresponds to x minus 4. And then plus or minus 3i, basically it's just x squared plus 9. Now, these are imaginary zeros. They would not be in that list. Now, even though you see a 3 there, that's just kind of a coincidence. Now, before we move on here, there's something else I want you to do. I want you to find out f of 3 for that polynomial above. So f of 3, let's see what f of 3 is going to be. Well, that would be 3 to the third minus 4 times 3 to the second plus 9 times 3 minus 36. And what do you get for that? You get negative 18. Now, here's something really interesting. I want you to now divide f of x by x minus 3. And look at the remainder. You're going to find something really neat here. So we have 1, 3 times 1 is 3, that's negative 1. Negative 3, that will be 6. 6 times 3 is 18. Negative 18. This is not a coincidence. This basically talks about synthetic. Not only can we use this to synthetically divide, synthetic substitution. Now I know I misspelled substitution. So yeah, so you can actually do, I think this is kind of cool to do synthetic substitution. All right, I want you to try this next one. All factors of negative 12 over factors of 2. So basically, plus or minus 12, 6, 4, 3, 2, and 1. And then you would just divide over 2 by 2 and then 1. So we can quickly simplify this. So let's see here, 12 over 2, well, that's 6. 6 over 2, it's 3. 4 over 2, it's 2. 3 halves. 2 over 2, which is 1. And 1 over 2, 1 half. Let's see, 12 over 1, that's 12. 6 over 1 is 6, we already have that. Then we get 4. We already have 3 in here, we already have 2. So now we're going to find all the zeros using methods learned previously. So I think I'm going to try graphing this. I mean, I could do all sorts of methods. So let's see what we get here. There we go. 2x to the third plus 7x squared minus 7x minus 12. So if we see here that negative 4 is one of our roots. Okay, so what we're going to do here, we'll use the first one. We could have used the others, but let's just use -4. So 2, 7, -7, -12. The remainder has to be 0. Let's see, that's going to be -8. And that'll be a -3, +12. So the depressed quadratic is 2x squared minus x minus 3. And you set that equal to 0. dq, I say depressed quadratic. Now, if this was a 4th degree, we would have to bring out 2 of the roots, 1 by 1. But not in this case yet. So let's just factor it. So the sum is going to be -1, and your product's -6. So let's see what we get. That will be -3 and +2. 2x squared minus 3x plus 2x minus 3 equal to 0. X times 2x minus 3 plus 1 times 2x minus 3 equals 0. 2x minus 3, x plus 1 equal to 0. Oh. So if 2x minus 3 is 0, 2x is 3, x is 3/2. X plus 1 equal to 0, x equals -1. So x equal to -4, that corresponds to a factor of x plus 4. X equal to 3/2 corresponding to a factor of 2x minus 3. And then x equal to -1 corresponds to x plus 1. All 3 zeros are rational. Are they in the list? -4, 3/2, and -1. All right. And if I really wanted to, so let's see, -4, -1, and 3/2. Now the other thing I could do is type this in factored form, x plus 4, 2x minus 3, x plus 1. And see how they're the exact same thing? And since they're the exact same thing, we know that that's the correct factorization. So, now they're only, all right, and we do. So, we do have a 0 where x is going to be 3. So we'll have 3, -19, 33, and -9. So that'll be a 3 there. That'll be a 9 here. So -10. That'll be a -30 for a +3. And then a 9 for 0. So now you have 3x squared minus 10x plus 3 equal to 0. Now, we're also going to do intervals of increase and decrease for this. Now, the difference is you just, you'll have to use the calculator. It's okay. Now, remember, intervals of increase and decrease are written in terms of which variable? X. So, now since this starts off with a 3, we need 2 numbers that have a sum of -10 and a product of +9. Well, -9 and -1. So let's see what we get here. So 3x times, that'll be x minus 3, minus 1 times x minus 3 equal to 0. And x minus 3 times 3x minus 1 equal to 0. Oh, that's interesting. So if we set each of these equal to 0, we actually get x equal to 3 occurring twice. So what happens here, so the zeros are x equal to 3, which does occur twice, and x equal to 1/3. Now, the factored form would be x minus 3 squared times 3x minus 1. Now, how can we verify that? Well, that's actually very easy to do. We can use the graphing calculator, which I'm actually going to change some values here. Ah, perfect. So, and here's the other thing. Well, let's see, this would be x minus 3 quantity squared, and that would be times 3x minus 1. And let's see if we get a match, and we do. So, here's what we're going to do now. I'm going to copy this over, and if I can get this stupid thing to work, we need to find our extreme points. So, here's the thing. This is a max, and this is a min. You know, there's two turning points. And OneNote has just quit on me. Oh, all right, you better work. All right, let's see. Come on. All right, so we've got to find the maximum and a minimum. So here's what we'll do. We'll go to second calc, and we'll choose maximum. Now, this spider needs to be anywhere to the left of this maximum. And guessing that don't, and just hit enter. We get 1.2, 1.22. And we'll run to 2 decimal places, 8.43. Now the minimum, let's see where the minimum is. And you're going to find something very interesting. So second calc, and this time we're choosing the minimum. And now we want to make sure that this spider is somewhere to the left. Hit enter, then we'll take it somewhere to the right. This is at 3. So this 0, x equals 3. Now how many times did that 0 occur? It occurred twice. And so it's also going to be an extreme point. Since x equals 3 occurred twice, it's an extreme point. Well, there is to it. So basically it's increasing. So the intervals of increase go from negative infinity to 1.22 union with 3 to infinity. And then it's decreasing from 1.22 to 3. Now, here's, end behavior. Forgot to write that up. That's actually real easy. As x goes, so end behavior. As x goes to negative infinity, where's y going? Negative infinity. And as x goes to positive infinity, y is going to positive infinity. Now, here's the thing. The domain is basically all reals. And since the end behavior goes off in opposite directions, so is the range. Negative infinity to positive infinity. So we've answered quite a bit here. All right. All right, so here's the thing. So let's put in a 4 here. We'll have 1, -2, -19, and then 44. And so we have 1, that's a 4 here, so that's going to be a 2. That'll be an 8, so that'll be -11, and then -44. So we have x squared plus 2x minus 11 equal to 0 that we would have to solve. So if we do that, let's just complete the square. Half of 2 is 1, that squared is 1. X plus 1 quantity squared equals 12. We square root both sides, and that is going to be plus or minus 2 root 3. So x will be -1 plus or minus 2 root 3. Now, if we go here, -1 plus 2 root 3, we get a 0. -1 minus 2 root 3, we get a 0 for that. So we will write this in factored form. Now, x equal to 4 and x equal to -1 plus or minus 2 root 3. So this is x minus 4, and this is just x squared plus 2x minus 11. And we definitely don't want to write, this is the factored form. Now, if I go here and type in x minus 4 times x squared plus 2x minus 11, and what we're doing here is we're verifying that they're the exact same thing, and they are. Now, so we're going to determine the end behavior. So for the end behavior, what happens as x goes to negative infinity? Where's y go? Negative infinity. What happens as x goes to positive infinity? Positive infinity. Very good. Now, this one is going to have 2 extreme points. This is a max, and this is a min. Now, we're going to actually use the calculator to figure this out. And we'll round it to 2 decimal places, and I'll make it clear that that's what I want. So if we go to the, not the trace, but second calc, let's figure out the maximum here. So I need to have my spider somewhere to the left of that boundary. And then somewhere to the right, I'm going to bypass the guess. So then we hit enter, bypass the guess, and we get negative 1.94. And that is 66.03. Now for the minimum, let's figure that out. And again, we're using the calculator. And no, there is no way to do this without the calculator. Well, there is. You have to use calculus. You learn calculus. After this is pre-calc. So take it to the left. And we take it to the right. 3.27 and negative 4.55. So basically, it is increasing, even though, remember, intervals of increase and decrease, read them left to right. So it's increasing from negative infinity to negative 1.94, and then we start decreasing from negative 1.94 all the way to 3.27. But after the 3.27, we start increasing again. And we don't stop until infinity. Now, domain and range are very easy for this. Domain is all reals for any polynomial. And for the range, since this polynomial has opposite end behavior, these max and min points are not the absolute max or min. In other words, they're local extreme points, so the range is all reals as well. And that is what you will get for this. All right, so let's find this minimum here. Now, the thing is, this minimum is not just the local minimum. This is going to be the absolute minimum. And it would be, this minimum here would be at 0.2 and negative 13.5. And this is, again, the absolute min. Now that's going to come into play for our domain and range. Now we have a maximum and a minimum point right here. These are just locals. So let's find this maximum. So we'll take it to the left. And we will take it to the right, just a little bit over to the right. And we get 1.68 and 0.22. That's a local max. And this here is a local min. And you're going to find something very interesting about this minimum in just a few seconds. So I'm going to have this spider very close to it. It's going to be at to 0. Now, so, and what you'll see is, yeah, you will see that this had a couple of zeros here. So obviously x equals 2. Oh, let's finish off the intervals here. I'm sorry. So obviously it's decreasing, and then increasing, and then decreasing very shortly, and then increasing again. So we are decreasing from negative infinity to 0.2, and then 1.68 to positive 2. We are now increasing from 0.2 to 1.68, and then from 2 to infinity. Now, the domain is going to be all reals. Now, the range is going to go, this is the absolute minimum, so basically negative 13.5 to infinity. And since this is an even degree, as x goes to positive and negative infinity, y is going to positive infinity. That way. Now, we obviously have x equal to 2 as one of our roots. So here's what's going to happen. We are going to do this, where this over here. So what happens here for this, we're going to bring this down, and it's going to be 6, negative 31, 49, negative 16, and negative 12. So 6 here, 2 times 6 is 12. This will be negative 19, negative 38 here, so that's going to be 11. That'll be 22, that'll be 6, and that'll be 12 for 0. Now, we have a depressed cubic. Now, what we can do is, this is our cubic. That's 6x to the third minus 19x to the second plus 11x plus 6. Now, let's graph that one instead, but we have to work from that cubic. We're not going to break this apart using, starting with the 4th degree one. So that would be 6x to the third minus 19x to the second plus 11x plus 6 was plus 6, yes. And let's see here. Choose a root of that. So basically, here's what's happening. The fact that 2 is a root of that twice, basically that means that x equals 2 had a multiplicity of 2. Now, so we have to do another one. This time x equals 2 So then 6, negative 19, 11 and 6, 12, that'll be negative 7, negative 14, that's negative 3, negative 6 and 0. So x equals 2 occurs twice. Now, 6x squared minus 7x minus 3 equal to 0. The sum is negative 7, and the product is negative 18. Those are negative 9 and positive 2. So 6x squared minus 9x plus 2x minus 3. I can take a 3x out of this. I get 2x minus 3. And then plus 1 times 2x minus 3. 2x minus 3 times 3x plus 1. X is going to be 3 halves. X is going to be negative 1/3. So there's our 4 zeros. Now, consider this. This occurred twice. So the ultimate factorization in any order would be x minus 2 squared times 2x minus 3 and 3x plus 1. Now, before we end it, let's see that they are the same thing. So I shouldn't have deleted that 4th degree one. I don't know what I was thinking. But we'll fix that. Watch. 6x the 4th, not the 5th, the 4th. Minus 31x to the 3rd plus 49x to the 2nd minus 16x minus 12. Now, if we write the factored form, well, first, let's go back to this. Now, the factorization in any order, 2x minus 3, 3x plus 1, x minus 2, quantity squared. You get a match. All right, I am going to start going over this. So what we can do is we need to find 2 of the zeros in order to bring this down to a quadratic. So one thing I'm going to do is I'm going to use the root finder. And now here's the thing. When you go to the 4th order, it gives you options, you know, the A plus BI and decimal, yeah, it's not going to give you them in simplest form. So we'll enter the coefficients, which are 6, 1, negative 233, 434, and 392. Solve it, and I see that negative 7 and 4 are zeros. Now, here's what's going to happen. Now, x is going to equal negative 7, and x is going to equal positive 4. So what we are going to end up doing here, we're going to take out the 7, negative 7 right now. Now, again, whenever you do the synthetic division, the remainder should indeed be what? 0. So 6, negative 7 times 6, that's negative 42, negative 41. Oh, I'm going to have to use a calculator here. I can't do that. Well, I don't want to do it in my head because if I screw up, so that's 287 get 54. Multiply that by -7, we get -378. And we get 56 out of this. And 56 times -7 is -392. Now, so what has happened here is we now have a depressed cubic of 6x to the third minus 41x to the second plus 54x plus 56. Now, what you're going to find is -7 is not going to be a zero of this because we've already stripped it down, so to speak. So what will happen then, here's a neat little thing. We're going to take this depressed cubic and pull out a 4. So that 6 stays intact. That will be 24. -41 plus 24, that is, I believe, -17. That's going to be -68 for, yep, that will be -14. -14 times 4 is -56. So now, from this, what we get out of it is now 6x squared minus 17x minus 14. Now that we have a quadratic, we can now solve that. And then ultimately write the whole thing in factored form. So, and again, you got to set it equal to 0. So what I'm going to do here is I'm going to use the quadratic formula. Now, by the way, you do not have to memorize it because I will give it to you. So we want to figure out the discriminant. Let's see, that's -17 squared minus 4 times 6 times -14. I mean, it's true, you have to factor this, but the quadratic formula has been so lonesome. I'm wondering, like, Mr. Jarrett, why haven't you used me? No, not really, but 625 for that. And the square root of 625 is 25. So we get 17 plus or minus 25 over 2a. Well, that's 12. So 17 plus 25, that's 42 over 12, which is 3.5 or 7/2. And 17 minus 25, well, that's -8 over 12. Well, that's going to be -2/3. So what we're going to do is we're going to write this in factored form. And again, when you take your test on this, I'm actually going to give you a page to do all the work that you may need to do. And when it comes time to write this in factored form and what have you, you will be able to do that. You know, you'll be able to just outright do it. So the zeros were x equal to -7, x equal to 4, x equal to 7/2, and x equal to -2/3. So we're going to put those into factors. We're going to make factors out of them. So how do we do that? Well, that's very easy to do. If x is -7, well, that means it's just x plus 7. X equal to 4, well, that's just x minus 4. Now, x equal to 7/2. Now, if you factor this, you won't need to do this. I mean, plus, I'm not going to make you show me the work for it. But what we would get here is 2x equal to 7. So basically, you get 2x minus 7. And then the last one, well, we get 3x equal to -2. Or 3x plus 2. This, my friends, is our factored form. And how can we verify that we got this right? Well, let's graph it. Watch this. X plus 7, x minus 4, or in any order, FYI, 2x minus 7, and 3x plus 2. Boom! Look at that. So the factored form has shown that we got this all right. Now, let's talk about the graph here. Now, it's a 4th degree. This is the absolute minimum. And that is going to have an impact on the range in just a few moments. This is a local max. And this is a local min. Now, the thing is, how many turning points can a 4th degree have up to? There's 3. 1 less. And so if it's 1 less, yeah, it can have at the most 3. So we need to figure out, we'll round the x values to 2 decimal places. We'll just take the whole number for the y values. So let's do this. Second calc, a minimum. We're going to do this first one. Take it to the left. Then take it to the right. Yes. Yes, so we get negative 4.87 with a y value of negative 39.88. Now that is going to have an impact on our range. Now local max, let's find that maximum. So we're going to take it somewhere to the left. Let's not take it too far, somewhere close. There we go. We'll take it to the right. Coaster's made it over the hill. 0.99 and 600. Now we shall do the local min. So this time, a minimum somewhere to the left. Okay, that's good. Somewhere to the right, 3.76 and negative 18. Now we've gotten our extreme points. Now, The intervals of increase, well, let's see here. Starting here, it's decreasing. So we'll actually start off with it decreasing from negative infinity to negative 4.87. Then it's going to increase from negative 4.87 to 0.99. Then decreasing from 0.99 to 3.76, and then from 3.76 on, we're increasing. Now, bless you. For the end behavior, as x goes to negative infinity, where's y going? To positive infinity. When x goes to positive infinity, where's y going? Positive infinity, it's going up. Because it's a positive leading term of even degree. All right, the last part that I want to talk, domain. Well, domain's a given. Domain of any polynomial, all reals. However, the range, if we take a look at our graph, we see that the absolute minimum is at negative 39.88. So it will start at negative 39.88 and go to infinity. Right back, don't worry. All right, so one of the first zeros that we're going to look at for this one would be negative 1. So let's see, that's a negative 1, 12, negative 55, 72, and 140. So that'll be a negative 1. That'll be a 1 for 13. That'll be negative 13 and negative 68. That'll be positive 68. Wait, I messed up. Let's see. Negative 13. Oh, wait, yeah. That is 140. And negative 140 for 0. So basically, we do get a 0 here. And we do get another 0, 1, 2, 3, 4, 5. Well, let's verify that 5 is a 0. It is. So we're now going to strip off the 5. This will be a negative 1. That will be a negative 5 for a 8. That'll be a 40 for negative 28. And then negative 140, and that'll equal 0. So we get negative x squared plus 8x minus 28 equaling 0. Come on. All right. Now let's divide out by negative 1 here because I do not like having a negative in front of that. So we're going to get x squared minus 8x plus 28 equal to 0. X squared minus 8x will then equal to negative 28. We're going to complete the square. Half of negative 8 is negative 4. That squared is 16. So here's the thing. Why I only went through twice is because two of those zeros are imaginary. That's why. So this becomes x minus 4 quantity squared equal to negative 12. We square root that. X minus 4 will equal plus or minus, let's see, square root of negative 12 is I times 2, 2, and 3. 2i root 3. So x will equal 4 plus or minus 2i root 3. Now, if you use the root finder, you probably found two zeros that had all this funky decimal action with it. Well, yeah, we're basically going to do this. We're going to get this. Now, these are conjugates of each other. Now, the other thing is, by rule, since we only had two real zeros, technically, the rule is the number of turning points is the number of real zeros minus 1. Now, I'm never going to make you memorize that, but the fact is, this is just the absolute max. So basically, factored form would be x plus 1, x minus 5. I'm not going to wait here, huh? I know the problem. Negative x squared plus 8x minus 28. Or I could just take a negative 1 out. I would accept either one because, well, I'm not. Neither is my wife. That's why she married me. Nah, she married me because she loved me. So I tell myself. All right, so that's what we get for that. Now, basically, for the end behavior, as x goes off in both directions, y is going to negative infinity because, oh, bless you, it's an even degree and a negative leading term. Domain is all reals. Now the range is going to depend on what that maximum point is. Let's figure it out. Let's take it to the left and then take it to the right. And to the right. .89 and 168. So the range will go from negative infinity to 168. It's increasing from negative infinity all the way up to, what's that x value? That is 0.89. And decreasing from 0.89 to infinity. All right, not bad. Not bad at all. We're going to put it right back. Give me. All right, let's go ahead and start talking about this. So I see that negative 1 and 2 are appear to be zeros of this. Well, let's double check. Negative 1 is a 0 and 2 is a 0. So we're going to take those two out right now. So we get 1, negative 7, 33, negative 17, and negative 58. So let's see, negative 1 times 1 is negative 1, that's a negative 8, that's a positive 8, that's a 41. That is negative 41 for negative 58. For positive 58, we get 0. Now, if you did the 2 first, that's okay. But I'm going to do the 2. 2 times 1 is 2, negative 6. That would be negative 12 for 29, for 58, and 0. So now, x squared minus 6x plus 29 equals 0. Now, we can already realize that this is going to generate some imaginary zeros because, well, when I complete the square, x squared minus 6x will equal negative 29. Half of negative 6 is negative 3. That squared is 9. And x minus 3 quantity squared equal to negative 20. Square root of negative 20 would be 2i root 5. So x minus 3 will equal plus or minus 2i root 5. X will equal 3 plus or minus 2i root 5. So, with that in mind, the factored form would be x plus 1, x minus 2, and x squared minus 6x plus 29. We're going to have an absolute minimum here. Let's see what it is. .28 and negative 60. We're decreasing here and increasing here. So basically for the n's, since it's even degree, as x goes to plus or minus infinity, y is going to go to infinity. The domain, all reals. The range will start at negative 60 and go to infinity. We're increasing from 0.28 to infinity, decreasing from negative infinity to 0.28. All right, not bad. Is we have to, you can't just do x minus 3/7. I've had some students that will do that in the past. So what we need to do is to convert each of these to factors. Now, how many factors can we multiply together at a time? We can only do 2 at a time. So what we're going to have to do is basically take any 2, multiply them together. Now, for this one, we'll get a second degree out of it, but then we'll have to multiply it by a third factor. Now, this one is x minus 3. This one is x plus 2. So let's multiply this out. Well, that's easy. X squared minus 3x plus 2x minus 6. And we get x squared minus x minus 6. Now, we're not done yet because we have to multiply by this other factor. Well, we need to get rid of the fraction first. So we're going to multiply both sides by 7 and get 7x equal to 3, or 7x minus 3. And since that is the factor, we should make a table. So we'll do this, 7x minus 3, x squared minus x minus 6. So x squared times 7x is what? 7x to the third, or 7x cubed. We get negative 7x squared out of this, negative 42x, negative 3x squared, positive 3x, and positive 18. So ultimately, we get 7x to the third minus 10x to the second minus 39x plus 18. Now, one thing we can do, we can put that into the root finder and verify it. Let's see what happens. Root finder, we're going to go back to third order. And let's see what happens. So we get 7, negative 10, negative 39, and 18. There they are. All right, awesomeness. Now for this next one, you're going to have 4 zeros. So do 2 at a time. I'm going to let you try this.
Ever since this whole COVID thing, I can't do it. I used to sleep till like 12 or 1.
I don't go to bed till about, I didn't go to bed till about 3 hours at 5:30. I'm so tired.
All right, so here's what we're going to do. Notice that it said x equal to 5 with a multiplicity of 2. So what that means is that it occurs twice. So what happens here, what we're going to do here, obviously this is x minus 5, and this is x minus 5. So what we'll do here is we'll multiply these 2 at a time. Now for this next one, I multiply by 3, I get 3x equal to negative 4, or 3x plus 4. Multiply out by 7 here on both sides, and I get 7x equal to 2, and then 7x minus 2. So what I'll do here, I will multiply 2 of these together, and then I'll multiply the products at the end. Well, for this one, this is easy. I get x squared minus 10x plus 25. And for this next one, I would get 21x squared plus 28x minus 6x. That would be 22x. Oh, this is going to be some big numbers. That's okay. So now, this is going to be a fun one. Well, it's not. It could be worse. I could give you, more to do. But I'm not going to. So x squared minus 10x plus 25. 21x squared, 22x, and minus 8. So this is 21x to the fourth, 22x to the third, negative 8x squared, negative 210x to the third, negative 220x to the second, negative 80x. Now 21 times 25, I got to use a calculator because, well, you know what, I could do it without it. I think it's actually, you know what, forget it, I'm using a calculator. 525x squared. 25 times 22, well, that would be 550x. Is that right? Yeah. Huh, I still got it. Minus 200. Now, here's the neat thing. Kind of a tic-tac-toe thing. Like terms on the same diagonal. So I get 21x to the fourth. Let's see, negative 210 plus 22, that would be negative 188x to the third. Let's see, 525 minus 220 minus 8, 297x squared. And that would be plus 470x minus 200. I should really have written it down in one long line like this. All right, not bad. So I'm going to let you try the next one. So for this one, x equal to 2/3, well, that means 3x will equal 2, 3x minus 2. Now, here's the thing. We have some imaginary zeros. So what we got to do here is, obviously 4 minus 3i root 7. Now, 4 plus 3i root 7 must also be a 0. So basically, the sum of these two is 8. And the product is, well, let's use the calculator. 4 minus 3i root 7. And the other one is 4 plus 3i root 7. And that's going to be 79. So the equation that results from this is x squared minus 8x plus 79. So we have 3x minus 2, x squared minus 8x plus 79. So that's 3x to the third minus 2x to the second minus 24x squared, 16x, 3 times 79, that's 237x, and negative 2 times 79 is negative 158. So we get 3x to the third minus 26x to the second plus 253x minus 158. We can do that whole sum and product rule. So negative 2 plus 4 root 2, negative 2 minus 4 root 2, you have negative 4 minus 5i root 7, and you have negative 4 plus 5i root 7. Well, the sum of these is negative 4, and the product, well, let's see what the product is. I'll use my calculator. Negative 2 plus or root 2. We get negative 28. So basically, this is x squared plus 4x minus 28. Now the sum here is going to be negative 8. The product, I'll use my calculator, negative 4 minus 5, root 7, negative 4 plus 5 by root 7. And that product is going to be 191. So this is x squared plus 8x plus 191. So we have to multiply these two bad boys together, and we're going to get some big numbers out of this. X squared 4x minus 28, x squared 8x 191. So we get x to the 4th, 8x to the 3rd, 191x to the 2nd, 4x to the 3rd, 32x squared. Well, 4 times 191, that's 764x. Negative 28x squared. That would be negative 224x. And negative 28 times 191 is negative 5,348. So for this one, we get x to the 4th plus 12x to the 3rd plus 195x squared plus, let's see, 764 minus 224, that's 540x minus 5,348. All right. So rational functions are of the form f of x equaling p of x over q of x, where p of x and q of x, neither of them could equal 0, since the denominator is simply not allowed to equal 0. That's going to give us some domain restrictions here. So that's something we definitely don't want here. So what we need to do in either of these cases is set the denominator not equal to 0. And then we'll solve, and then we'll put them in interval notation, which, believe it or not, that's a lot easier than it looks. So x squared minus 9 cannot equal 0. So in order to do that, that's just a simple difference of squares factoring, and that's going to factor into x minus 3 and x plus 3 not equal to 0. So basically we get x minus 3 cannot equal to 0, and x plus 3 cannot equal to 0. So basically x cannot equal 3, nor x could equal negative 3. Now, going from this to interval notation might be a little tricky. So basically, if we put negative 3 and positive 3 on our number line, and we put these down, basically it can include everything except those values. And since it'll include everything except those values, we've got our restrictions So basically, the interval would go from negative infinity to negative 3, union with negative 3 to 3, and lastly, union with 3 to infinity. Let me redraw that last one as a parenthesis. A little nicer. There it is. All right. So for this second one, x squared plus 6x minus 27 cannot equal 0. So we can factor this and you get x plus 9 and x minus 3 not equal to 0. So basically, x plus 9 can't be 0, nor could x minus 3 be 0. So x cannot be negative 9, x cannot be positive 3. Bless you. So if we map our restrictions, we have everything except the negative 9 and the positive 3. But everything else is good. So the interval will go from negative infinity to negative 9, union with negative 9 to 3, union with 3 to infinity. Now these rational functions at the most will be second degree or quadratic. It won't be third degree, because that's just a little, it's not that it's too much. It's just, it's, keep the idea basic here. Now for this last one, x squared plus 16 cannot equal 0. Now, this is a sum of squares. Now, a sum of squares does not factor over the integers. So basically, x squared cannot equal negative 16. X cannot equal plus or minus 4i. But these are not real. So the domain, consequently, becomes all reals. So yeah, so if you get imaginary numbers in your domain restrictions, well then there are no domain restrictions, because these rational functions deal solely with, we're only going to be having those deal with real numbers. Just real numbers for that. Get back here. So now we're going to talk about the very basic reciprocal function f of x equal to 1 over x. So if you graph it on your calculator, it's going to look something like this. It's not going to be perfect, but this is going to be pretty close. That's not this. Try that again. Okay. So here's what happens. Oh, I should have. All right, here we go. So if we go to 1 over x, yeah, it looks exactly like this. Now, if I hold the trace button down and I go over to the right, the y value just keeps getting smaller and smaller. And it's going to eventually, it's going to approach. Think of a plane that just keeps flying closer and closer to the ground, but never quite gets there. That is an example of a horizontal asymptote. It's an imaginary line, or kind of a guide So this is a horizontal asymptote, or an HA of y equals 0. Now, when we have a rational function, another type of asymptote these will have is a vertical asymptote. And this is x equal to 0, vertical asymptote. Now, if you actually go to trace and try to type in 0, you get nothing, which this function is actually undefined here. It's undefined at this vertical asymptote. So basically, next to this vertical asymptote, we'll call it a VA of x equals 0. What that tells us is the domain is just simply x not equal to 0. Or basically negative infinity to 0 union with 0 to infinity. Now, the range of these, which we are not going to really talk about, range is technically everything except 0. But we're not going to focus on range. When it comes to these rational functions, we're only going to focus on the domain and not the range. All right, so a couple of interesting things here. Limits and arrow notation, the end behavior. This also has to do with end behavior. As x goes out to both positive and negative infinity, now for the first time, y is not going to go to positive or negative infinity. Instead, this y value is going to go closer and closer to 0, which this is not a coincidence. This is the horizontal asymptote or the end behavior. Now, what you could do is, if you zoomed out a couple of times and typed in a random value like, 25, see, it's just going to get closer and closer to 0. Now, it's not going to quite reach it. It's just going to get so close that basically it'll be in scientific notation. So that's how the horizontal asymptote works. Now, for the vertical asymptote, let's look at the behaviors around that. Now, as x approaches 0, now this minus sign means it is from the left. Now, make sure you know your left from your right. So, when it's approaching 0 from the left, y is approaching negative infinity. Now, this is behavior around the asymptotes. Now, as x approaches 0, if you see this is from the right. So from the right side, it's going to approach infinity. Now, I'm not going to make you write that out. Basically, it's going to be a fill-in. It's going to be like fill-in questions and whatnot that ask you to do this. So, All right, so basically what's going to happen is this numerator is going to factor into x plus 1 and x plus 5. Now, the denominator is going to factor into x plus 1 and x plus 7. So what happens here is we're able to eliminate something, and we get the equivalent of x plus 5 over x plus 7. So what happens, the domain, we still have two restrictions. Even though this factor was eliminated, it still must be included in the domain exclusions. Now, there is going to be a special thing with that, which we'll talk about shortly. And x plus 7 cannot be 0. X cannot be -1. X cannot be -7. So basically, -∞ to -7, union with -7 to -1, union with -1 to infinity. Now, when you go to graph this, if I try to type in -7, I get a restriction. Now, if I go to type in -1, I still get a restriction, even though there doesn't seem to be an asymptote there at -1. It's still a restriction. Equation approaches a domain exclusion from either side. So here's the thing. If we have 1 over x minus 5, well, you know what? Let's graph that on the calculator. And make sure you have the fractions set up, because I have seen way too many students do this. What did I do wrong here? I should have put that x minus 5 in a parenthesis. Yeah, you'll make a mistake. And it happens. So basically, this needs to be 1 over x minus 5 as a parenthesis. So basically, yeah, that's what it looks like ultimately. So what happens here, if we have x minus 5 equal to 0, x equaling 5, this, my friends, is a vertical asymptote. So asymptote is kind of a type of, just kind of a stencil. Think about it as a stencil, if you will. So basically, this means the domain is everything except 5. Now, until I say otherwise, we will have a horizontal asymptote of y equals 0. Again, the horizontal asymptote is never going to be, it's not going to be anything other than 0 until we come up with the rule. So, given that these are our asymptotes, the graph will nearly follow these asymptotes. See, yeah, this is the only thing that I do not like about this. Close enough. So, again, these asymptotes are just kind of a stencil for the graph. Now, we can make sign diagrams basically, this line x equals c is a vertical asymptote if x approaches c from the left or c from the right. F of x will go to positive or negative infinity. And this power, this what appears to be a power, it's just saying from the left or from the right. And when you have a lab assignment or a test on this, basically you're going to be given the information like as, it'll look like this: as x approaches blank from the left, f of x approaches what? Well, or as x approaches blank from the right, f of x would approach a blank. So this blank here is going to be a 0. So x, whenever it's approaching, from the left or from the right, now these are your vertical. This is your vertical asymptote. So as x approaches 0 from, well, it's not 0. What was the vertical asymptote in this case? It was 5. So basically, we're approaching 5 from the left and 5 from the right. 5 from the left, f of x goes to negative infinity. If it's 5 from the right, we're going to positive infinity. And as x approaches positive or negative infinity, y is going to approach what? 0. And so, yeah, basically, you'll be given this, and this would be a blank. All right, so in our previous function, yes, it's clear that that is our domain. X equals 5 is our vertical asymptote. So why does it approach that? We can make a sign diagram. We don't even really need to do that so much here. Now, critical values that we speak of will be all zeros, whatever make the numerator equal to 0. Well, in these cases, there aren't any right now. There will be later on. We're going to keep this as easy as, we're going to keep it simple right now. We're going to do everything for this one. This one, we have f of x equals 1 over x plus 7. Well, that means we're going to have a vertical asymptote where x is equal to negative 7. X equals negative 7. So basically, this is what you're going to get for this. And if you can use the graphing calculator to help you come up with this. 1 over x plus 7, and yep, it's going to look like this. So we have the vertical asymptote. We also have the horizontal asymptote of y equals 0. That still has not changed anything. Now, that actually gives us one of our answers here as it pertains to the end behavior. As x goes to positive and negative infinity, y goes to 0. There's your asymptote. Boom. Now, As we go to negative 7 from the left, we're going to negative infinity. And negative 7 from the right, we're going to positive infinity. Well, here's the thing. Something less than negative 7, like negative 7.01, would that make this positive or negative? To the left. I would make that negative. That's why it works this way. Just trying to tell you how it works. All right, so we've got, this one's going to have 2 vertical asymptotes. All right, so now you do whatever you need to do. Comes out of this. So x squared plus 12x plus 35 equaling 0. Well, this is, and by the way, I am never going to give you one where, like, you're going to have, like, 2 plus 3 root 5 for asymptotes. Asymptotes and zeros will always be rational numbers. This I swear. So x plus 7 and x plus 5 equaling 0. So basically, x plus 7 equal to 0, and x plus 5 equal to 0. So we get our vertical asymptotes. Negative 7 and negative 5. So if we go ahead and just draw them, now we have one for negative 7 and one for negative 5. Now our horizontal asymptote is still 0. That's going to change possibly by the end of today. Now, so basically the domain, x cannot be negative 7, nor can it be negative 5. And in interval, negative infinity to negative 7, union with negative 7 to negative 5, union with negative 5 to infinity. Now, if you look here, the graph is going to look something like this. So the behavior at the asymptotes is a little bit different because there are 2 here. So as we approach negative 7 from the left, we go to positive infinity. And negative 5 from the right, we're going to positive infinity. But negative 7 from the left and negative 5 from the left, we're going to negative infinity. And our horizontal asymptote, or that end behavior, is still 0. So yeah, we could actually make a sign diagram. I'm not going to focus on sign diagrams for this. I can just make a quick one here. Basically, your numerator and your denominator. Well, let's see here. Here's negative 7 and negative 5, which are restrictions here. So for the negative 7, well, This is 1 over, that's negative. Now this is positive, and that's positive. Now, for the negative 5, that's negative on both sides here, and that's positive here. So this is positive, negative, and positive. So basically, negative 7 from the right, that's why this is positive. Negative 7 from from the left. From the right, that's negative, and negative 5 from the left. Bless you, that's negative as well. I'm not going to make you do this, but I just thought it was kind of a cool way to show you how it all worked. All right, we're going to take our 10, and so what I want to do here is, so basically, what you need to do here is, anytime you get a rational function that looks something like this, you want to factor everything that you can. So this numerator is still going to be x minus 5, but this denominator is x minus 5 times x plus 8. And ultimately, the x minus 5s are factored out, so we get a simplified version of 1 over x plus 8. However, even though this factored out, x minus 5 still cannot be 0. X cannot be 5, and x plus 8 cannot equal 0. X cannot be negative 8. So the x minus 5 was what was factored out of both the numerator and the denominator. Now, we still get 2 domain exclusions. And if we actually tried to type in negative 8, we get nothing. There's a vertical asymptote there. But for 5, we don't see an asymptote there. So it's like, oh, what the heckaroonie do we do here? Well, here's what happens. We only get one vertical asymptote. And that's going to be x equals negative 8. And let's see, if the behavior is similar, and so our horizontal asymptote is still 0. That still is not changing. So there's only one vertical asymptote. Now, why that is simply because where the domain restriction where x was 5 was factored out. So the only vertical asymptote was x equals negative 8. So if we trace that and got x, did the trace and got x equals 5, we get an error. Now, the value where x equals 5 is considered a whole. So the whole of the function, it occurs wherever there is a domain exclusion, but it is not a vertical asymptote. Not a vertical asymptote. So can we find the y-coordinate of the whole? Yes, we can. So obviously, that was x minus 5 times, over x minus 5, x plus 8. Ultimately, it's simplified to 1 over x plus 8. So basically, you plug x equals 5 into the simplified version. So if you plug x equals 5 into the simplified version, where x is 5, we get 1 over 13. So 5 and 1/13, 1 over 13 is the whole. Now, a decimal equivalence of 1 over 13 would be 0.0769 and change. Now, why did I point that out? Well, you're going to see why in just a minute. Because, obviously, when I go to trace and I type in 5, I get nothing here. But if I did 4.999, look at that y value. It is very close. So that's what we get. So any values of x that are excluded from the domain end up having to be wholes or vertical asymptotes. After that, any values that make the denominator 0 are vertical asymptotes. So here is the simplified version. So x equals -8 is a vertical asymptote. So that's how it all comes together. And we've looked at vertical asymptotes and wholes in much greater detail. We're now going to talk about horizontal asymptotes. A horizontal asymptote is of the form y equals c, and basically that is your end behavior. Now, unlike vertical asymptotes, we're really unconcerned with the behavior around horizontal asymptotes. Now, there are 3 possibilities for a horizontal asymptote. Now, this second case has been the case the whole time, where the degree of the numerator is less than the degree of the denominator. By rule, horizontal asymptote is just y equals 0, boom, that's it, you're done. End of story for that. Nothing else to report. Boom, gone, bye. Now, if we have this, if the degrees are the same, then the horizontal asymptote will be the quotient of the 2 leading terms. So we're going to end up coming up with a problem. We're going to see a problem shortly where that's the case. Now, the third case, and this is a very special case, if the degree of the numerator is greater than that of the denominator, there is no horizontal asymptote. Instead, the graph's end behavior will be the same as the graph of the quotient, disregarding the denominator. And the end behavior will resemble a linear equation called a slant or oblique asymptote. Now, regardless of the case, vertical asymptotes will occur wherever the denominator equals 0. And I want to add a disclaimer in the simplified version. And that's an if you have to simplify it. X-intercepts are wherever the numerator is equal to 0. The y-intercept occurs wherever x equals 0. Well, hey, guess what? You've already seen that before. Now, we can find both vertical and horizontal asymptotes as well as any zeros. Now, critical points will include x-coordinates of holes, vertical asymptotes, as well as any zeros. And whenever we do an inequality based on this, which we will do either this or next week, the inequalities are going to be so easy for rationals. Like, you're going to be like, wow. So, also to make things easier at this point, nothing involving complex, imaginary, none of that crap is going to be used in rational functions. Every critical value, zero, intercept, or whatever will be a rational value. No radicals, no imaginaries, nothing of that sort. Everything will factor. Why? Well, it's easy this way. I could throw in that, but I figure why not? Try to make it as painless as possible. All right, so we're going to do this one together. Now, I have a list of things, and now in the rough sketch, basically I don't leave you a blank graph. And the reason is simply because there's just no need to. I'm just going to do a rough sketch here. And we're not going to worry about a sign diagram. But, I mean, they are, yeah, let me just say, I will not require. So, basically, you need to set your numerator equal to 0 and your denominator equal to 0 and solve. Obviously, nothing is going to simplify, so you will be left with no holes. So yeah, the numerator is 4x minus 3, and the denominator is 2x plus 5. So when we do that, now this is also going to be our very first one where the horizontal asymptote is not 0. What I'm going to do is I'm just going to kind of copy it over to this as the rough sketch. All right, so if I have 4x minus 3 equal to 0, obviously that means 4x is going to equal 3. X is going to equal 3/4. Now, if I go and type in 3/4 for x, I get 0. So basically, there is a 0 where x equals 3/4. The ordered pair would be 3/4 and 0. And yep, right about here. Now, we're going to set the denominator equal to 0. 2x cannot equal, 2x equals -5. X will be -5/2. So, we have a vertical asymptote at x equals -5/2. And if we go to type it in on the trace, -5/2 Yeah, we get nothing. Now, that also gives us the domain. We have only one domain restriction, and negative infinity to negative 5/2, union with negative 5/2 to infinity. So if we graph this line, negative 5/2, there it is. There's our vertical asymptote. Now, our horizontal asymptote is not y equals 0. Instead, for the horizontal asymptote, we take the ratio of the leading terms. What is the leading term in the numerator? Yeah, or 4x. How about for the denominator? 2x. Well, that just simplifies to 4 over 2, or 2. Y equals 2. There is your horizontal asymptote. Of y equals 2. Now, if you actually go into the graph and hit trace and hold this down, it's just going to keep getting closer and closer to 2. All right, now, so we've gotten our asymptotes. There's the rough sketch. Oh, the y-intercept. Well, that's easy. Let's see, that would be 4 times 0 minus 3 over 2 times 0 plus 5. So negative 3/5 or 0, negative 3/5. And if we go to the trace, type in 0, and get that. There's our y-intercept. Now, I am going to include the template for behaviors. So as x approaches from the left and from the right, y is going to approach what and what, and as x approaches positive, negative, infinity, y will approach what? So, our vertical asymptote was in fact negative 5/2. So negative 5/2 from the left. Are we going to positive or negative infinity? Positive, very good. And how about negative 5/2 from the right? Negative infinity. And as x goes out to positive or negative infinity, what does y approach? 2. There you have it. All that to factor our numerator, and we're going to end up factoring our denominator. So this one is going to have a sum of 13 and a product of negative 140. So 20 and negative 7. So you get 4x squared plus 20x minus 7x minus 35. So if we take a 4x out, we get x plus 5. We can take a 7 out of this, and we get x plus 5. X plus 5 times 4x minus 7. Now, let's putz with the denominator. That is x squared plus 4x minus 5. Well, that's simply x plus 5 and x minus 1. So, what's going to happen here is our numerator, x plus 5 and 4x minus 7, our denominator is x plus 5, x minus 1. X plus 5s are canceled out, and we have 4x minus 7 over x minus 1. So, we have a vertical asymptote wherever x minus 1 is 0. Well, that's wherever x is 1. Right there. Now, our horizontal asymptote, we can look at either the original version, 4x squared over x squared, or 4x over x. Either way, it is y equals 4. Now, we had a removal of a factor, so what this means is we are going to have a hole where x equals negative 5. So, the y-coordinate is 4 times negative 5 minus 7 over negative 5 minus 1. Well, that is negative 27 over negative 6. So negative 5, and that would be 9/2. So there's a hole. Now, a 0, we only have one factor that we have to set equal to 0. If we set 4x minus 7 equal to 0, 4x will equal 7, x will equal 7/4. So, if we actually type in 7/4, there's a 0. Now, our domain, we had the two restrictions. X cannot equal negative 5, and x cannot equal 1. I'm not going to make you do the interval for this. Now, the whole, so our vertical asymptote was at 1. So the behavior from the left, it would go to positive infinity. From the right, it would go to negative infinity. Now, this other restriction is simply the whole. Nine-halves. So if I go to type in something close to negative 5, like negative 5.00001, yeah, see how close it is? Now, as x goes to positive and negative infinity, y is going to go to 4. Now, I will give you room to work, but basically I will have places where I ask you to put everything. All right. So, now all this stuff that you're being being asked to find, now one thing, you won't be asked to do it, I mean, like in this order here. But we do have to consider a few. So basically, I'm going to take this in many different orders here. So if we set the numerator equal to 0, now ordinarily you would also be expected to factor if these were quadratics. But this is going to tell us a few things about the problem. So what we have to do is set the numerator and the denominator each equal to 0 and solve. Now, the numerator, now 5x equals -2, x is going to be -2 over 5. And if you look at this, -2 over 5, what you'll see is, yeah, that's a 0. That is, in fact, a 0. So, a 0 or x-intercept at x equal to -2/5 or -2/5, 0. You could write it either way. Now, for this second, for the denominator, 3x minus 4 equaling 0, well, we get 3x equal to 4, x equal to 4/3. Now, since that is what makes our denominator equal to 0, we have a vertical asymptote at x equal to 4/3. So that is not only a vertical asymptote, but obviously a domain restriction. And if we actually go to trace and type in 4/3, we get nothing. Now, so far, we have a vertical asymptote here. Well, that's going to tell us what the domain is. Now, again, when you are given this on a problem set or a test, you will have room to do whatever work you need to do, and then you'll have specific spaces like the domain here. X-intercepts or zeros here. Now, we have one domain restriction. X cannot equal 4/3. All right. So, now we've gotten the domain, we've gotten vertical asymptote, we've gotten zeros. Let's now do the horizontal asymptote. Now, this is going to be the first one where it's not 0, and it's pretty obvious that the horizontal asymptote is not 0. So what you have to do is simply take the ratio of the leading terms, which is 5x over 3x, and it's going to be 5/3. Or, y equals 5/3. So there is your horizontal asymptote. So you see basically how this function uses these asymptotes as a stencil. That's how it all works. Now, we've done all of that. Now, the y-intercept, well, that's really easy. The y-intercept is where x is 0. So basically, y equals 5 times 0 plus 2 over 3 times 0 minus 4. That would be -1/2. So 0, -1/2. And if we put 0, yeah, there it is. Now, so there's your y-intercept. Now, if we do the behaviors, x approaches one from the left and one from the right, y will approach something there and y will approach something here, and x will go to positive, negative, infinity. So our vertical asymptote was indeed, what was it? 4/3. So 4/3 from the left, well, that's going to negative infinity. 4/3 from the right, that's going to go to positive infinity. Now, as x approaches positive or negative infinity, what does y approach? 5/3. Very good. Now, I am actually going to do the kill two birds with one stone thing. And, this is everything here. Basically, what I would do on a test, what I'm probably going to do is I'm actually going to give you like one or two of these, and then you'll solve a rational inequality that is very similar to this. So for the inequality, that was 5x plus 2 over 3x minus 4 greater than or equal to 0. Now, we have to discuss, our critical points. Now, the criticals come from zeros or domain restrictions. And so basically, we did have a 0 at negative 2/5. And we had a vertical asymptote, x equal to 4/3. So here's the thing. If we put this on a number line, now, negative 2/5 will go here. Now, would this circle be filled in or left open? We would fill it in because it came from a numerator. Now, the other one was 4/3. Now, that one is going to have to be left open because that would give us a denominator of 0. You can't have that. So basically, the function itself, 5x plus 2 over 3x minus 4. So we have 3 sections to deal with. Now, FYI, if we had one with a hole, I would not have you do the inequality because, we just wouldn't worry about an inequality if it had a hole. So let's see here. So we know the 5x plus 2 changes at negative 2/5. So our numerator to the left of that would be obviously negative, but to the right, it's going to be positive. Now, our denominator changes at 4/3. So what happens here, obviously it's negative to the left and positive to the right. Negative divided by negative is positive, negative over positive, negative, and positives. Now, since we wanted greater than or equal, we want the positives. So, the interval, I would ask for this in interval notation. It would go from negative infinity to negative 2/5. That negative 2/5 would receive a bracket union with 4/3 to positive infinity. Because, yeah, this and that, because that 4/3 cannot be in any way included. Now, here's the thing. If I chose something to the left of negative 2/5, like negative 0.5, yeah, see, it's going to be positive. Now, if I choose something from, like, okay, 0. If I chose 0, well, I know for a fact that that's going to be negative. And, something greater than 4/3, like 1.4, it's going to be positive. So, in essence, we've actually saved ourselves quite a bit of time. Now, of course, is factor the numerator and denominator, or, you know what, we're going to factor it because we're going to see what happens here. So 2x squared plus x minus 15, well, let's see, the sum is 1 and the product negative 30. So 6 and negative 5. 2x squared plus 6x minus 5x minus 15. So 2x times x plus 3 minus 5 times x plus 3. This will factor into 2x minus 5 and x plus 3. So that's going to come back into play for us in a little while. But let's do the denominator. It's 3x squared plus 2x minus 21. The sum is 2 and product's negative 63. Well, that's going to be 9 and negative 7. So 3x squared plus 9x minus 7x minus 21. And we do factor by grouping again. I can take a 3x out. That'll be x plus 3 minus 7 times x plus 3. So you get 3x minus 7 times x plus 3. So now that is done, here's the thing. So f of x is going to equal 2x minus 5 times x plus 3 over 3x minus 7 times x plus 3. So the x plus 3's will be factored out, and that's going to leave us with a simplified version of 2x minus 5 over 3x minus 7. Now, that's going to come into play when we want to do the, do the whole. Because there will be a whole where x is 3 or negative 3. So it doesn't matter where you start it from. Let's do the horizontal asymptote first. So y would equal, well, you could do it from the original 2x squared over 3x squared, or 2x over 3x. it doesn't matter because we get a horizontal asymptote of y equaling 2/3. So y equals 2/3 is your horizontal asymptote. Now, we only have one vertical asymptote where 3x minus 7 equals 0. 3x will equal 7. X will be 7/3. So it'll be something like this. Now, we're going to have a hole. Obviously, x is going to be -3. The y coordinate will be 2 times -3 minus 5 over 3 times -3 minus 7. That would be -11 over -18. No, I think that should be -16. So 11/16. So -3 and 11/16 is the coordinate of the hole. Now, we only have one 0, where 2x minus 5 equals 0. X will equal 5/2. The reason is, basically, if there's a factor that gets factored out, it takes precedence at being a whole as opposed to being a 0. So that's why it'll work like that. And the y-intercept, well, that would just be 0 and 5/7. So before I know we don't, I'm going to condense this just a bit so I can write up our behaviors. So if we check this here, wrong one. So yeah, 0, 5/7, 5/2, that's a 0. Now let's see here. 7/3, well, that's going to be the vertical asymptote. And the hole was where x was -3, not -33, but -3. But if we did like -2.999999, we get 0.6875. What is 11/16 as a decimal? That's it. So, and again, let me keep reiterating. Basically, this would be typed out for you. And the only thing you'd have to fill in are blanks. So the two domain restrictions were 7/3 and -3. Now, -3, y value approached 11/16. Now, 7/3 from the left, it went to positive infinity. 7/3 from the right went to negative infinity. And as x goes to positive and negative infinity, what would y go to in this event? Two-thirds. And yeah, basically, if you let that be 10 and you kept it going, yeah, it's just going to get closer and closer to 2/3 without actually getting there. All right, so that's going to be it. So good news is, all right, so let's start off by doing some factoring. So for the numerator, the sum is going to be -8, and the product is going to be whatever 3 times -3 is, which is -9. Those numbers are going to be -9 and 1. So what will happen is you get 3x squared minus 9x plus x minus 3. So for the numerator, we can take a 3x out, getting us x minus 3. We can only take out a 1 here. And we'll get x minus 3 for this. X minus 3 times 3x plus 1 for that numerator. Now, let's do the denominator. So for that, well, that's actually very easy. X squared plus 5x minus 24, that is x plus 8 and x minus 3. So ultimately, what we're going to get out of the deal, f of x will equal 3x plus 1 times x minus 3 over x plus 8 times x minus 3. So, now that that's done, what we can do, obviously we're going to get some domain restrictions here. X plus 8 cannot be 0. X minus 3 can't be 0. So x cannot equal -8, nor could x be 3. And I've decided that the domain, you will not have to do an interval notation for this. Because, we just don't need it. So, now let's find some asymptotes here. Well, first, let's go back to the graph. If I were to type in -8, we get no response there. If I were to type in 3, we also get no response, even though there's no asymptote there. Well, because here's what happens. The x minus 3 is going to offset, or we're going to be able to factor out an x minus 3. So the simplified version is simply going to be f of x equal to 3x plus 1 over x plus 8. Now, since this x minus 3 was able to be factored out of the numerator and the denominator, we have a hole where x minus 3 equals 0. We have a hole where x is 3. But we need to figure out the y-coordinate of that hole. And for that, we are going to use the simplified version. So, f of 3 is going to be 3 times 3 plus 1 over 3 plus 8. Well, that's going to be 10 over 11. Now, 10 over 11 as a decimal is pretty close to 1. It's 0.909 repeating. Now, so what happens here is if we go to the graph and like do 2.99999, yeah, see we get that y value. Or if we do, 3.0001, oh yeah, we actually get 10 over 11. But yeah, this is what we get here. Now, so ultimately, the whole is at 3 and 10/11ths. Now, looking at the simplified version, we definitely see that we're going to have a vertical asymptote wherever x plus 8 equals 0. X equal to -8. So, x equal to -8, yeah, look at that. Now, it might be a little harder to see here, but if you did actually zoom out, yeah, you definitely see it, that it's there. But I do want to add that, when you take your test for this, everything that will be on there, everything would fit on a standard viewing window. So that's what we would get. All right, so we've got the vertical asymptote. Oh, we got a 0 wherever 3x plus 1 equals 0. X will equal -1/3. Or we could say -1/3, 0. And if we type in -1/3, you get 0. All right, so let's see what else we have. I think we need the y-intercept. Oh, let's do the horizontal asymptote. So the horizontal asymptote, we can take the ratio of the leading terms, which are, you could do it from the original, 3x squared over x squared, or 3x over x. But it just becomes 3. So there's your horizontal asymptote. Close enough. So that's our horizontal asymptote of y equals 3. And actually, if I were to zoom out, and if I were to do some heavy tracing, we see that y is just going to get closer and closer to 3. Oh, yeah. Yeah, it's going to get closer and closer to 3. All right. Oh, y-intercept. Well, that's easy. We can use the calculator. Now remember, the y-intercept is wherever x equals 0, 1/8. All right. So, and the other thing, I didn't put this on the notes, is x goes to something from the left, something from the right, something from the left, and something from the right. Now, this will be your domain restrictions. And as x goes to positive or negative infinity, y will go somewhere. So let's look at the vertical asymptote, which was -8. So -8 from the left and -8 from the right. Well, all you really got to do is look at the graph. -8 from, well, it's actually a little hard to see. So you might have to zoom out, or what you could do, yeah, -8 from the left, it's going to positive infinity. And -8 from the right, that's going to negative infinity. Now, our other domain restriction was where we had a hole, 3. And so from that, y is going to approach 10/11 for each of those. And as x goes to positive and negative infinity, where is y going to go? What is y going to approach? 3, horizontal asymptote. All right, so that's everything for that one. All right, so let's do a polynomial long division. We're going to divide x squared plus 2x minus 3 into x to the third plus 2x to the second minus 25x minus 50. Now, here is the nice thing. All you will need is the quotient. But we are going to do the remainder anyway. So, if I do x to the third over x to the second, well, that's x. So x times all of this, that's going to be x to the third plus 2x squared minus 3x, or negative x to the third minus 2x to the second plus 3x, and that goes. So we get an x here. Well, here's the thing. We get negative 22x minus 50 because we get nothing here. So this one was actually a lot simpler. It's not a horizontal asymptote, but it's a slant asymptote of y equals x. Don't worry about what the remainder is. Well, the remainder is 22x minus 50. Now, when you go to graph it, it looks really weird. Now, if you zoom out, look at that. Now, if we zoom out just once more, and we add y equals x, see, it looks so much more like this. And for that matter, if I do some tracing, the y values are just so close at this point. Like 65.45, 65.11. So, yeah, that's how a problem like this is simply going to work for you. Now, I will tell you, the one I give you on your test will have a slant asymptote of the form mx plus b. So it won't be like a perfect one, but it'll be like y equals x. So to factor this, well, let's do 5x squared minus 7x minus 6. The sum is -7, and the product is -30. Well, those numbers are -10 and +3. So last year we get 5x squared minus 10x plus 3x minus 6. So I can take a 5x out of these, and I get x minus 2. Take a 3 out of these, and then I get x minus 2. So x minus 2 times 5x plus 3. Now, let's do the denominator. So 2x squared plus 7x minus 4. The sum is going to be 7, and the product is negative 8. So our numbers are 8 and negative 1. So we get 2x squared plus 8x minus x minus 4. I can factor a 2x out of these first two, and I get x plus 4. And since that's negative, I can take a negative 1 out, and I get x plus 4. So for this, we get x plus 4 times 2x minus 1. So here's the thing. There are no holes. Why am I able to automatically come up with that? The fact that there are no holes. Nothing was able to be factored out. So x minus 2, 5x plus 3 over x plus 4, 2x minus 1. So yeah, no holes. And that's why you see what appears to be 2 vertical asymptotes. So let's go ahead and break this apart. Let's do the horizontal asymptote first. Now, y would equal 5 over 2. Remember, it's just the ratio of your two leading terms. Now, we get 2 vertical asymptotes. We have vertical asymptote where x plus 4 will equal 0, and 2x minus 1 equaling 0. X will equal negative 4. And so I'm going to graph that. You see how these vertical asymptotes, how these asymptotes are a stencil for the graph. And x equal to 1/2. Now, with the vertical asymptotes, we could actually come up with our domain. We get 2 restrictions. X can't equal negative 4, nor can x equal 1/2. All right, so we've gotten all that goodness. Let's see what else we got. Oh, zeros. Zeros slash x-intercepts. Basically, where x minus 2 is 0, 5x plus 3 is 0. So x will equal to 2. X will be negative 3/5. And if we go to the graph will corroborate that. 2 and negative 3 over 5. And while we're doing that, let's do our y-intercept, 3/2. Or, you could just say y equals 3/2. I would accept it either way. Now, so we've got everything done here except the inequality. Now, the inequality, believe it or not, is actually going to be very simple to do. Whenever we did the inequality for quadratics, we had to find the what? What was it that we had to find for quadratic equations? We had to find the roots. So for the inequality, basically you look at all critical values. And what are meant by those are domain restrictions and zeros. So there are going to be 4 critical points. Now, let's do this, we'll put it in factored form. So for the numerator, that numerator was x minus 2 and 5x plus 3. The denominator was x plus 4 and 2x minus 1. Now, the 4 critical values, so let's see here, the critical values, let's see, we had our vertical asymptotes at -4, so -4 is going to be our first one. Now, even though the inequality is saying greater than or equal to, why do I not fill this one in? Because it's an asymptote or a domain restriction, it cannot equal -4. Now, this -4 corresponded to which factor? Corresponded to x plus 4. Now, our next critical value down the line, let's see, -3/5. -3/5. Now, since that is from the numerator, we can fill that in. See, this all should look oddly familiar to you. So we're actually going to get a sneak preview of this. Now, the -3/5 corresponded to 5x plus 3. Now, our next critical value was 1/2. And we're not going to include that because that was a vertical asymptote. Now, the 1/2 corresponded to 2x minus 1. And last, but not least, 2. And since that was a 0, we can include that. And so we can make our sign diagram now ever so easily. Now, there are going to be 5 sections. Now, let's do this first one, x minus 2. Well, that obviously corresponds to this 2. So to the right, it will be, but to the left, it'll be negative. And the other thing is, yeah, the signs will alternate the same way, like they always have. So that's nothing new. Now, 5x plus 3, well, that corresponded to -3/5. So to the left, that's negative. To the right, we're positive. Now, x plus 4, which corresponds to -4. So to the left, we're negative, but to the right, we're positive. And last but not least, the 2x minus 1, which corresponds to a half, obviously negative here and positive here. So 4 positives makes this positive, negative, positive, negative, positive. So yeah, the signs alternate exactly the same way. Now, we wanted f of x greater than or equal to 0, so which ones do we really want? Do we want the positive or negative? We want positive. So the interval would go from negative infinity to -4, union with 3/5. Now that 3/5 gets a bracket because it is included, but what about the 1/2? That is a parenthesis because it's not included. Union with, well, 2. Now, will the 2 get a parenthesis or a bracket? Bracket to infinity. So basically the remainder, when we get into the inequalities, it's going to be like cruise control for you. Now, one thing we could also do, we could check something that is less than -4, -5, that's positive. Now, in this interval, in this next interval from -4 to -3/5, if I tried, I don't know, -2, we get a negative number. That's not what we wanted. Something between -3/5 and a half, 0. See, we get a positive out of that. So that's how it all works. All right, back together. All right, so what we can do with these rational functions, we can also transform them. Now, guys, are we can get back to you here? Come on. All right. Now, we can take a basic rational function and transform it using horizontal shifting as well as vertical shifting. Now, I'm not going to push that as much here because I'm basically going to show you how it works both ways here. And we're only going to do domains here. So, the original one, horizontal shift is if we have x plus or minus h on the bottom, and the plus k would be whatever you get on the outside. Now, there are vertical stretches, but we're not touching that. So, for this one, you shift the standard hyperbola 1 unit right and 2 up. So, here's what happens. Our standard vertical and horizontal asymptotes are x equal to 0 and y equal to 0. Now, for the magic of graphing, what I'm going to do is I'm going to show you how this shifts. So, we're going to take this whole thing and shift it 1 1 unit to the right and up by 2. And that's all we get here. Now, so now our horizontal asymptote is y equals 2. Our vertical asymptote is x equal to 1. Now, here's the thing. What makes this equal to 0? What value of x makes that equal to 0? What makes this equal to 0? Positive 1. Now, what we are going to do here, now 1 over x minus 1 plus 2 over 1, we're going to combine this into one single rational expression. And you're probably thinking, yeah, that's nuts. Why are we doing this? Well, I have my reasons for doing everything we did. So we have 1 plus 2x minus 2 over x minus 1. And we get 2x minus 1 over x minus 1. So, from this, our horizontal asymptote, 2x over x. What's 2x over x simplify to? Is 2. And we get the same exact vertical asymptote. So, we're able to see this 2 different ways. Now, I'm not going to do all of these because, frankly, if we're going to do some others, we're only going to do this next one, and then we're going to go on to word problems. So, what I need to do is I need to shift this 3 to the right and down by 1. So, now if we actually combine this, minus 1 over 1, we put an x plus 3 here. So 1 minus x plus 3 entirely over x plus 3. You get negative x minus 2 over x plus 3. Your horizontal asymptote is y equaling negative 1. Because negative x over positive x, that's negative 1. That's all. So I think there's a question or two about this on your MyLabs, but not, I'm not putting this on your test or anything. But I wanted to kind of talk about it anyway, real quick. All right, we're going to get into the word problems. Word problems are, you think they're tough, but they're actually very straightforward. Now, so remember that distance equals rate times time. So, now a commuter drives to work a distance of 40 miles, and they return home on the same route. Now, what happens here is the average velocity on the return trip was 25 miles per hour slower than the drive up due to the inability of people to drive. So express the total time required to complete the round trip as a function of average velocity on the outgoing trip. So, we can call this, big T of x. The distance is 40 miles. What we want to do here is basically solve this for time. So to do that, that is just distance over rate. So our distance is 40 miles. And if we we assume the speed on the outgoing trip. Now, this is the outgoing trip. But, your commuting time, you have to do, when you do an outgoing trip, obviously you have to do a return trip. So 40, but instead of dividing it by x, what are you going to divide this by? X minus 25. So guess what? You've figured out the function. Yeah. So, obviously, we're dealing with our system, miles per hour. 40 miles each way. So, if the drive up had an average velocity of 70 miles per hour, so the total time would be 40 over 70 plus 40 over 70 minus 25. And we do a little math here. We get 1.46 hours. That's how much time you spent anyway. Company started here, fantasy, is going to manufacture home theater systems that come in a box with not a 1080p, not a 2160p, but we're going 8640p. 8 times the resolution. 8K resolution. I think the best resolution you can get is actually 4K, like 4160. Yeah, 8K. And basically, I don't see how it could be any better than 1080p. You see the what? Wow. I mean, like when I would watch football on 1080p, I could see the blades of grass.
Like how clear your TV is?
Like resolution.
Okay. I was gonna ask the same.
Because, if you go to YouTube, like, you can watch videos like the standard definition is either 240 or 480p, or you can, and that depends on, you can choose the resolution for buffering purposes. Now, since I just have a standard monitor, it makes no difference what the resolution is. Now, so we're going to go Blu-ray 22.2 channel speakers. Oh, this is going to be like the home theater deluxe. Now, the monthly cost will be $1 million, and each unit will cost $2,500 in parts. So the monthly cost includes the labor that is needed. These are labor intensive. So the cost function, we'll call this C of X. X number of home theater systems, well, it's going to be 1 million plus 2,500X. So this basically this $1 million is like that's your overhead cost. You could call it. And this 2,500 is the per unit cost. So let's think about that, per unit. Now, the average cost function of producing X number of home theater systems, we can put a bar above this. Basically, we would be taking the cost function and dividing it by the number that we make. So basically what it means is the more of these we make, the average cost goes down. 1 million plus 2500x over x. Now, yeah, I actually had some students, it was in stats. I had a student that claimed that when he was putting numbers into the calculator, he was getting errors because he was putting the commas in. You don't do that. Well, that's why, yeah, well, that's what happens. So 1,000,000 plus 2500x is, divided by x. So if we make 50 of these, well, we're going to make up to 10,000. 1,000,000 plus 2,500 times 50, and then we're dividing that by 50. So when we do that, that is 22,500. Now, what this cost is when 50 units are made, the per unit cost is $22,500. Now, when you do this for 500, 5,000, and 10,000, you're going to see some drastic differences. So I want you to do this. So if we make 500 of these, the per unit cost has plummeted to $4,500. If we make 5,000 of these, the per unit cost has fallen to $2,700. Now, if we make 10,000 of these, the per unit cost is $2,600. So here's the thing, we doubled this. We would have expected the cost to go even lower. So, yeah, these are the per unit cost. Now, the horizontal asymptote for this. If we did a horizontal asymptote, 1,000,000 plus 2,500x over x. Now, remember, the horizontal asymptote, it's y equaling 2,500x over x. So y is going to be 2,500. So the per unit cost will not get lower than 2,500 bucks. Now, so if these home theater systems are sold for a cost of $10,000, now how many would we have to make to break even? So basically take 1,000,000 plus 2,500x over x and set that equal to 10,000. Now, of course, so here's the thing, we put a 1 under that and just cross multiply. Now, of course, we don't really want to break even. What do we really want to do? We want to make a profit. We want profits. Why? Well, why be in business if you're not making profit? What's that? Yeah, well, non-profit, yeah. So, $1 million equals 7,500x. So if we just take this million and divide it by 7,500, you get 133. Now, that's if we sold them at $10,000 a piece. Now, if we made 133 units, it would cost $10,000 a piece to make them. But obviously, if they are that special, we're not going to sell them at $10,000. What would we probably really sell these for? Maybe $20,000. That's a lot of money. All right, so that's going to do this. That's going to do it for this. Now, we're going to get back into inequalities. So, guess what? They're back. So, what you're going to do, first thing we need to do is solve the related equation. X to the third minus 3x to the second minus 54x plus 112 equal to 0. So what we're going to do is, I believe all the zeros will be rational for this. But, I will give you one of these with irrational zeros because, well, it's more fun that way. So, if I go to graph it, that's x to the third minus 3x to the second minus 54x, and I believe that's plus 112. So I do see 3 rational zeros. Like one of them is at -7. So what we're going to do is we're going to divide. So obviously x equals -7. So what we're going to do is divide by x plus 7. So put a -7 in here, we get 1, -3, -54, 112. Now the remainder should be 0. -7 times 1, well, that's -7. We get -10. That is going to be 70. And -7 times 16, well, that's -112. Boom. So, x squared minus 10x plus 16 equals 0. Now, yeah, it's true. Yeah, these zeros are all rational. It'll all work out. But you might be given ones with irrational zeros, no imaginary zeros. So this will become x minus 8 and x minus 2 equaling 0. So if x minus 8 is 0, well, that means x equals 8. If x minus 2 is 0, that means x is going to equal 2. Now, so how many factors or how many zeros did we have for this? We had 3. Now, the first one was -7. And since it was less than or equal to, we fill in the dots. Our next one is 2. Our last one is 8. And so the corresponding factors, x plus 7, x minus 2, x minus 8. So for the -7, which corresponds to x plus 7, to the left, it's negative, but to the right, you're positive. Now for x minus 2, to the left, you're negative, to the right, you're positive. And then x minus 8, to the left, you're negative, to the right, you're positive. So 3 negatives means that it is negative. A negative and, a positive and 2 negatives mean it is positive, 2 positives and a negative. Negative, and then positive. So just like with those rational ones and quadratics, the signs alternate. Now, which one did we want? We want a negative. So, here and here. So the interval would be from negative infinity to -7 bracket union with 2 to 8. Now, if I did something less than -7, such as, -8, it's negative. Something between -7 and 2, 0. Positive. So you get the same thing. All right, I'm going to let you try this next one. And to graph this, we get x to the third plus 10x squared plus, that's 10x squared plus x minus 120. So when I go to graph it, I see I have a root at -8. So -8 is one of my roots, which is the same as dividing it by x plus 8. So we have 1, 10, 1, and -120. So we get a 1 here, -8 times 1, that's -8. That'll be a 2. That'll be -16, -15, and then positive 120. So x squared plus 2x minus 15 equaling 0. That is x plus 5 and x minus 3 equaling 0. So x will equal -5 and x will equal 3. So what we'll do now is we'll plot those on a number line. So remember, -8, which corresponded to x plus 8. Now, here's the thing. Am I going to fill that in or leave it open? I have to leave it open. X plus 5, well, that'll correspond to -5. I'm leaving them all open. So, yeah, and truth be told, yeah, the sign altering, the altering signs comes back into play here again. That is just not going to stop. The only time that that would be an issue is if we had a 0 that occurred more than once. And we're probably going to encounter something like that, so be ready. So, negative, positive, negative, positive. Now, since the inequality was greater than or equal, I wanted positive. So the final answer would go from -8 to -5, union with 3 to infinity. All right, so before I dismiss you, all right, so the first thing we need to do, as always, is factor. So let's factor the numerator. So for this one, the sum is -1, and your product is -12. So the two numbers are -4 and +3. So 2x squared minus 4x plus 3x minus 6 is going to equal 0. We do our factor by grouping. We can take a 2x out of this, which gives me x minus 2 plus 3. Multiplying that by x minus 2 equal, well, it doesn't really matter. I mean, yeah, we could set it equal to 0 or not. But for the numerator, we get x minus 2 and 2x plus 3. Now for the denominator, that's 3x squared minus 19x plus 20. The sum for this is -19, and your product is +60. Oh, well, that's -15 and -4. So 3x squared minus 15x minus 4x plus 20. So I can take a 3x out of this, giving me x minus 5. And I can take a 4 out. It has to be a -4, which will indeed give me x minus 5. So ultimately, the denominator will become x minus 5 multiplied by 3x minus 4. So what happens then is our f of x function has been factored into x minus 2 times 2x plus 3 over x minus 5 times 3x minus 4. So the big question here before we keep moving here, are there any holes? No holes. So in other words, yeah, so no factors were able to be factored out. And because of that, yeah, so what we're going to get here is we're going to get 2 vertical asymptotes, and we're going to get 2 zeros. So our vertical asymptotes are wherever x minus 5 equals 0 and 3x minus 4 equals 0. Well, we get a vertical asymptote of x equal to 5, 3x equal to 4, x equal to 4/3. And so, yeah, you see, 4/3, well, it's right, fits there pretty nicely. And then x equals 5. 1, 2, 3, 4, 5, right here. There you go. And as I said before, I am not going to require the interval notation or domain. So basically, since we have our vertical asymptotes, consequently, we get our domain restrictions. X cannot equal 5, nor could x equal 4/3. And again, when you see this on your test, you're going to have a bunch of room to do all of your work. And I just want the final answers, in their places, for easier grading. Although I'm down to 9 in my other class, I'm down to 3 here. I remember one semester where I had like 40 tests to grade. That took a while. So there's our domain. There's our vertical asymptotes. Let's do the horizontal asymptote. Well, it's going to be the ratio of your leading terms, which is 2x squared over 3x squared. So basically, y will equal 2/3. And it'll look. And so, yeah, the asymptotes are kind of like a stencil for the graph. Now, when it comes to the range, which is the y values, yeah, you could say that, well, some can argue, that the range would be everything except the asymptote, the horizontal asymptote, but it actually does cross it here. Now, there are cases where it doesn't, but that's okay. Now, we have 2 zeros to deal with. So, zeros are wherever x minus 2 equals 0 and 2x plus 3 equal to 0. Well, x equals 2, or you could say 2, 0. X equals -3/2, or -3/2, 0. So 2, 0, and -3/2, 0. And if you actually do this, yeah, 2, 0, and -3/2. So the inequality is going to be very easy to do at this point, at this juncture. So, oh wait, I forgot the y-intercept. Well, that's easy. It's where x is 0, -3/10. And I'll just kind of throw that right here. So y would equal -3/10, or you could give it as a coordinate. All right, so yeah, rough sketch. Everything is shown there. Now we can do the inequality. Now, I know I've kind of jumped the gun on inequalities here. I did so with my other class as well. They're actually a little, yeah. So here's the thing. We'll make the number line, and then we'll come up with this in interval notation. And then we'll do our end behavior stuff, which, again, you won't have to write it out. You'll be filling in blanks, and I will leave you the spaces to do that. All right, so our numerator, x minus 2 times 2x plus 3, and our denominator of x minus 5 and 3x minus 4. So we need to come up with all of our critical points in order. Now, our first one is -3/2. Now, would that one be filled in or left open? Well, -3/2 corresponded to this. It was a 0. So we will include it. We will include this one. And -3/2 corresponds to this one. The next one down the line, let's see. That would be 4/3. Now, would that one be filled in or left open? That one is going to be left open because it's a domain restriction, or it comes from the denominator. And then we have 2. Are we going to fill that one in or leave it open? We're going to fill it in, and obviously it corresponds to x minus 2. And then the last one, which is 5, we leave that one open, and that corresponds to x minus 5. So, and the other thing here you probably realize with your sign diagrams is that the signs will alternate, especially for the rational ones. And the reason I can say that with certainty, I'm not going to have any like repeating factors or anything of that nature. Now, polynomials, that's where the game may change. So everything is negative here, and that's a positive one. Let's see, the 4/3, that's negative there, and that's positive here. I mean, again, for rational ones, yeah, the signs are just going to alternate. And then negative and then positive here. So this is positive, negative, positive, negative, positive. Now, which one did I want? I wanted the negative one because it was less than or equal to 0. So that's what I get. Now, it's true, you could have also done this on the calculator. You know, I'm not going to make you show the sign diagrams, but I think the sign diagrams make it buku easier. So the interval would go from -3/2 to 4/3. Now, -3/2 is included, but the 4/3 is not. And from 2 to 5. And then the very last, So the very last thing is going to be, you know, what happens around the asymptotes. And you'll be left with space, or around the domain restrictions, if it may be a hole. And when I write these notes, when I do this next semester, I'm actually going to include this. And this x goes to positive negative infinity, y will go to. All right, so our two vertical asymptotes were 4/3 and 5. So 4/3 from the left, negative infinity. 4/3 from the right, positive infinity. About 5 from the left. Negative infinity. And here's the thing. 5 from the left, the sign diagram also tells you what you would need. Which I think is kind of cool. And as x goes to positive and negative infinity, where does y approach? Yep, 2/3. Whoa, what's the h? It would go to 2/3, because remember, that's the horizontal asymptote. Okay, why is this doing this? Hang on. We're going to do a polynomial long division. Now, the nice thing is, all we have to worry about is the quotient. We actually don't really need to worry about the remainder. So we're going to divide 2x squared plus 5x, minus 5x plus 8 into 6x to the third minus 25x to the second plus 53x minus 48. So again, we do the liter by the liter. 6x to the third divided by 2x to the second, well, that's 3x. So, and then 3x times all of this times 2x squared minus 5x plus 8, that's going to be 6x to the third minus 15x to the second plus 24x. Yeah, like one perfect example. I've learned some things from students. That Logan Buzzard showed me this, and that has made my life so much easier. Like, so you get negative 10x squared, and 53 minus 24. That would be 29x minus 48. So that's going to be a minus 5. Now, technically, that's it. But let's figure out the remainder anyway, just for a giggle. So, 10x squared plus 25x minus 40 plus 10x squared minus 25x plus 40. So we get a remainder of 4x minus 8. So the slant asymptote is y equal to 3x minus 5. And that's all I'm going to ask you for. So here is what happens. Let me show you. When you graph this function, it's kind of hard to see. So this is where one of the few times we would actually need to zoom out. And if I actually type in 3x minus 5, see, it basically mimics that behavior. Now, yeah, it looks like a line, and partially because when I originally came up with examples like these, like they would have zeros and all that. But slant asymptote is kind of, in my opinion, its own thing. And that's the way it needs to be. And it's going to remain that way for way. All right. All right, so what we're going to do, we're going to factor this numerator and denominator, and I'll tell you what, you guys, just fact. I'm just going to give you the factorizations here. So the numerator is going to factor into 3x minus 7 and x plus 2. And the denominator is going to become 4x plus 3 and x plus 2. So we are going to have a whole. So we're going to have a whole where x is, well, x plus 2 equals 0. So x is going to be negative 2. Now, since that's where our first whole, well, only one whole, ultimately this function would simplify into 3x minus 7 over 4x plus 3. So the y value would be 3 times negative 2 minus 7 over 4 times negative 2 plus 3. So that would be negative 13 over negative 5, or 13/5. So basically, you have a hole at negative 2, 13/5. Now, if we go to the function, if we go to the graphing calculator real quick, yeah, negative 2 is definitely a domain restriction. If I do like negative 1.999, yeah, it's for negative 2.0001, yeah, 2.6. Now, the next one, we're going to have a vertical asymptote at where 4x plus 3 equals 0. So x will be negative 3/4. And we can see that plain as day right here. So the domain is everything, x cannot equal negative 2, x cannot equal negative 3/4. So we have a horizontal asymptote. We can use either the original one or the simplified one, but it is going to be y equal to 3/4. So that's where that one's going to be. And we're going to have a 0 where 3x minus 7 equals 0. 3x will equal 7. X will be 7/3, or you could say 7/3 and 0. Y-intercept, let's see what the y-intercept is. Negative 7/3. That's interesting. That is the inverse of that. Don't think that would ever happen. That's just a coincidence that that happened. Trust me. I'll try to devise a rule about that. So, yeah, that's what we get. Oh, there we go. Sorry. Understanding. And the behaviors around the asymptotes and holes. X approaches from the left, from the right, left, right. And x approaches positive, negative, infinity. Y will approach 3/4. Asymptote. Now, you did have one hole and one vertical asymptote. At negative 2, negative 2 from the left or right basically goes to 13/5. And let's see, our vertical asymptote was negative 3/4. Negative 3/4 from the left goes to positive infinity and negative infinity as we go at it from the right. Now, what that means here is we are going to shift this 5 units left, and this plus 4 is 4 units up. Now, nice thing is I'm actually going to be able to shift this 5 units to the left, and then 4 units up. So the asymptotes are moved with it. But the main idea here is this. 1 over x plus 5 plus 4 over 1. If we want to combine this to form one rational expression, the common denominator is just x plus 5. So we'll just do an x plus 5 and an x plus 5. So we get 1 plus 4x plus 20 over x plus 5. Or 4x plus 21 over x plus 5. Now, here's the thing. Our vertical asymptote is x equals negative 5. The horizontal asymptote was 4, y equals 4. But we can also see it as y equal to 4x over x. So this is just another way of seeing everything. So now we're going to move into another, basically what you have to do to get started is you start by solving 3x to the third plus 7x to the second minus 83x plus 105 equal to 0. So that's when, truth be told, all three zeros are going to be perfectly rational here. But remember those sign diagrams we did? Well, we're going to do those again for this. So what we can do is we'll do this. To graph this, and I have a good reason to graph it anyway. 3x to the third plus 7x to the second minus 83x plus 105. And what we need to do is determine one of these zeros. But this is going to help us when we do the inequality part. So I think negative 7 is one of the roots. Yes. So x equaling negative 7 is a root. So what we're going to end up doing is divide by x plus 7. So guess what? Synthetic division is back. You get 3, 7, negative 83, and 105. So that's a 3. That'll be negative 21, so that will be negative 14. 14 times 7 that's going to be 98. So that'll be 15. Negative 7 times 15 is negative 105, or 0. So basically what we have to do, we get 3x squared minus 14x plus 15 equal to 0, the depressed quadratic. And we're going to solve this one now. We'll factor it. So the sum is negative 14, and your product is 45. So let's see here. Oh, negative 9, negative 5. So 3x squared minus 9x minus 5x plus 15 equal to 0. So 3x times x minus 3 minus 5 times x minus 3 equaling 0. So we get 3x minus 5 times x minus 3 equal to 0. Now, before we actually go ahead and make our sign diagram, I'm going to go ahead and x equals -7. Obviously, that's x plus 7. Now, 3x minus 5 equal to 0. That means 3x is 5, x is 5/3. And x minus 3 equal to 0, x will equal 3. So, we have 3 factors to contend with. So, -7, which corresponds to x plus 7. Now, would I fill these in or leave them open? Look at the inequality. We're going to fill them all in. So then, 5/3, and then 3. So basically, yeah, the behavior of sign diagrams does not change. It's going to be the same thing where all 3 are negative, then so 3 negatives, and then 2 negatives and a positive. That becomes negative, and that becomes positive. Now, what we wanted, since it was greater than, we wanted the positives. Now, the interesting thing is, when we go to the graph for this, if I chose something like, -8, that's negative. That's not what we wanted. If I chose 0, so the graph, by picking points with the graph, that would corroborate what we had. So the interval would go from -7 to 5/3, union with 3 to infinity. That's what we get. What's that? Well, because -infinity to -7, that's where it is negative. And we needed it to be greater than. So that's why. Take the positive. If it's less than, you have to take the negative. All right, quadratic inequalities. So if we graph this, we see that we have one rational 0 of -1. Now the other 2 zeros are not going to be rational, but let's not let that fluster us. So if we put a -1 here, 1, 5, -10, -14. That was -1. Yep. So at first one, -1 times 1 is -1. That's going to be a 4. And that'll be a -4 for a -14. Then for a +14, this will be a 0. So you have x squared plus 4x minus 14 equaling 0. So we're going to complete the square on this one. X squared plus 4x will equal 14. F of 4 is 2. That squared is 4. So we get x plus 2 quantity squared equaling 18. Now, when we take the square root of both sides, you get x plus 2. Now, by the way, there will be no imaginaries for these because, well, imaginary roots will not work. So it'll be plus or minus 3 root 2. So x will equal to negative 2 plus or minus 3 root 2. Now, we have to put these on a number line and make sure they are in order. So, negative 2 minus 3 root 2 is obviously going to be smaller than negative 2 plus 3 root 2. So, you have negative 2 minus 3 root 2, which we'll call that A. Now, our next one is negative 1. Our last one is negative 2 plus 3 root 2. So yeah, negative 2 plus 3 root 2. Let's call that B. And they're all going to be filled in. So basically, we have x minus A, x plus 1, x minus B. So yeah, 3 negatives. Yep. So we have negative, positive, negative, positive. Now, since we had it as less than or equal, this is what we wanted. So ultimately, we go from negative infinity to negative 2 minus 3 root 2. Close it. We get a bracket. Union with from negative 1 to negative 2 plus 3 root 2. Close your bracket. And that's it. All right, guys.